debate about more about the CNRS policies regarding the center. So the only left to say you is welcome and enjoy this journey. Thank you.
So hello everybody. So this is really a great pleasure to be here. Thank you, Hector. I just want to add very few words about the real pleasure about the day we had yesterday, first for the 25th anniversary of CMM. In fact, CNRS is very proud to be part of this long journey. Now, long journey, so it's a sort of maturity for the lab. So perhaps to recall to all of you, older and younger people, CNRS is a huge organism of research. In fact, in the world, I think it's the most largest organism devoted to research in the world, with 32,000 people that are employed by the organism. And it has a real will to be part of, to invest into international labs. There are 80 international labs, and among these 80 labs, there are 14 in mathematics. Okay, so this is occasion, as Hector said, to meet together with the 6 labs in mathematics in both America. So just to know, so of course, this is a CMM. There's also one in Rio with Claudio, which is here, one in Uruguay, in Montevideo, with Françoise Dalbo, which is the director, and which unfortunately cannot be here. And also Geronimo, I don't know where he is, Geronimo, here in Mexico. And also Osgur in Vancouver, in the middle, and Emmanuel Royer in Montreal. So this is occasion to meet, to share what can be done in this international lab, and of course what also can be done in science, because this is very important to me and to CNRS Mathematics to recall that science is of course in the center of everything. That's why when we prepare all this week with Hector, this was, for me at least, very important that a part of the week is devoted to science. So, and to have talks, to share knowledge after drinking champagne and things like that. This is time for science. So enjoy your day.
Okay, then we are going to start this today sessions on all the area that we are working here and with our collaborators. Then welcome to this workshop. And the first talk of this workshop is going to be given by Terry Rockefeller. Then I will introduce Terry. You know, Terry Rockefeller is one of our distinguished associated researcher to CMM for some years already. He was awarded by doctoral honoris causa from the university some years ago. And he's also very famous because they say research, but also he has a couple of books, convex analysis on 70s and variation analysis, which are among the most cited book ever in mathematics. Then and it's an impressive number of papers in not only in optimization, variation analysis, but also in connection of application with economics, optimal control, and many other areas. He was awarded some years ago in the 90s for Neumann Prize, and then we mentioned Terry the connection with France, but I remember that you was when you were very young when you was visiting Grenoble from at that time, And then the connection between Terry and the French community and optimization have a long date, and they have been working for many years with the French community in optimization and variation analysis. So for us, it's really a pleasure to have Terry as a plenary speaker of these sessions, and then welcome Terry to his talk. He's going to talk about the composition and optimization. So Terry.
See, I wonder if this, yes, it's working. I wanted to follow up for a moment on what Alejandro said about my connection with France, since France is so well represented here. I, of course, started out in the United States, and I was working in what was then a new subject, optimization. But I had a pure mathematical background, although I was getting into a subject that was new and numerical. And I will give you some general indication about this in a moment. But I love to do theory and organize ideas. And in the United States, though, people were much more interested in computing and some kind of particular applications. But I found a kind of second home in France because it was a country where theory in mathematics was deeply appreciated. And I had a very wonderful connection with France for many, many years, and still do. So thank you, France, and your representatives who are here. So now this talk will get a little more technical in my subject as I go along, but since I understand that not everyone here is in my area, surely, I wanted to give some general ideas at the beginning that will help you understand how this area is different, and on the other hand, how it fits in. Let me just see which is going to work here. Yes, so what is different about optimization? Let's think about the history of it. The history of mathematics is full of huge changes caused by some major advance in knowledge. One of the most obvious, of course, is the coming of physics with Newton, who at the same time was inventing calculus. So a lot of the mathematics that we know as modern analysis came from evolution of physics. But there are other dramatic fields that were relatively new. Another good example is statistics and probability. The whole concept of a random variable, how incredibly sophisticated it is, and a probability measure, none of that would have existed classically. That's a sort of revolution of itself. So I'd like you to think about optimization as something that came about and brought something really different into mathematics. And the reason, historically there was optimization, but the kind that was really around was the calculus of variations, which was inspired by physics, Lagrangians and Hamiltonians and so forth. But what happened when computers came is it became possible to consider large-scale problems which didn't just describe how the world worked, like a model of the solar system, for example, but allowed decisions to be made. You could control something, organize something, manage something, decide how to do things. And those problems were distinctly different because when you are making a decision, you always have to worry about, there's so many side effects or needs, and you can't be too much, it can't be too little. You have one-sided constraints. You end up with a different kind of geometry. Everything is really different. And furthermore, this brought about a study of problems that are such of an enormous size that you really needed different ways to look at them. So what was really different about mathematics, I hinted on it a little at the beginning, that classical analysis, by which I mean basically the kind of mathematics that grew out of physics, everything is differentiable. And as we all know, there was a tendency for a long time anyway, that whenever you had a problem, you could just assume functions are differentiable as much as you want, and nobody bothered about that. But optimization is completely different. There are many things in optimization which are not differentiable, and a lot of it is caused by the need to take care of one-sided conditions, not two-sided things. And that meant, for example, that the concept of convexity became very important. When I was a student, and a long time in the early part of my career, so this is going back a long time in the 1960s, the convex functions were only studied from the point of view of norms in Banach spaces and how smooth the norms were, or how round the unit balls of the Banach spaces were, things like that. This was the whole theory. And there was also the theory of topological vector spaces, where convexity again played a role, but in terms of neighborhoods. But that's not at all the kind of convexity that came to be important in optimization. And what we now, in the subject of optimization, we know that the real big dividing line is between whether you have convexity or not convexity. It's completely different from classical ideas that it's what's linear or what's nonlinear, that's the major distinction. That's not the way it is in optimization. Another thing is we have to start considering set-valued mappings, or multifonction, as was the popular name in France. And when I was a student, you should never do that. The whole idea of a mapping or a function, it had to be single-valued, or nobody would look kindly at you. But we had to embrace all that. You have to have sets that depend on parameters. How do the sets move? How do sets converge? And then we had to have functions that can take on infinity values. Now that turned out, you'll see that in a moment, but that turned out to be very different, because what is the graph of such a function? A graph of a function, if it involves infinity values, it's not going to be a graph that's lying in a vector space. You can't deal with it in the usual way. So we have to pass to something else, epigraphs. You'll see it in a moment. And then what I found, what attracted me and got me so fascinated with this subject as a young person and turned me in there to life was that there's a kind of duality. There's duality all over in mathematics. It's one of the most beautiful things about mathematics. But there's this really different kind of duality. You can't solve an optimization problem without having an opponent who's trying to screw you up. There's something weird about it, almost metaphysical. So I'll try to explain a little of that at the beginning, just so you can get some idea of why this is different and so interesting. And I'm going to try to do this a lot in a kind of an economics computational setting. I'm going to get into some ideas of how you would solve large-scale problems, and I will explain that in some economics terms. And one of the reasons I've chosen that is working with people here, Alejandro and others at CMM, on economics-type topics. Game theory and so forth has been a big connection and a very important reason why I've loved coming here to Santiago so many times over so many years. So to start with, I just want to, this is just to give you an idea of why things are really different. So up in the upper right, you see a closed bounded convex sets. Convex sets don't need to be closed, they don't need to be bounded, although for my purposes, I just about always want one to be closed. Even a hyperplane, the whole space is empty set, these are all convex sets. But here I've shown a convex set, and the definition, of course, of convexity is if you take any 2 points in the set, then the line segment joining them must also belong to the set. But there's a duality to it. A set that has that property can also be described dually as an intersection of closed half spaces, finite or infinitely many. And then that leads to something which you can already see the beginnings of a different kind of a calculus. So when we learn the calculus, we are thinking of things like the graph of a function, and then you could say linearize the graph, or you could take the normal to the graph. Somehow from the normal to the graph, you could recover the gradient of the function. Well, or you have, say, the geometry of classical analysis is like differential geometry. You can have tangent spaces and normal spaces. Well, here's where this goes in a different direction, a one-sided kind of direction. Take this little corner point in the upper left of that set C. There's the one thing we call the tangent cone. Now that's like a convex set, and it's like this. Well, try to shade it off to the left. Off to the right from that. You see this thing like a cone with its apex at this x1. That's a tangent cone. On the other hand, there's this normal cone. The normals, these are one-sided normals in the sense of convex analysis, and these two convex cones are polar to each other. This is a generalization of orthogonality between subspaces. So you can have a whole geometry based on this and the duality of it. All right, then what about a convex function? Well, as I explained, the graph of a convex function, if you wanted to have infinity values, and you'll see in a moment why I want infinity values, it wouldn't be in a vector space. So what we look at instead is the epigraph. So here it's a set of points on or above the graph, and the function, convexity of the function means geometrically that the epigraph is a convex set. Then once you have that, well, okay, that convex set has tangent cones and normal cones. Well, then you can start to develop a sort of calculus of subgradients and subderivatives out of all that. So and another thing is, when is this epigraph a closed set? That exactly corresponds to lower semi-continuity, a half of a. So we get involved very much with one-sided continuity. So that's just to give you a little flavor, because then we've learned how to go beyond convexity with all these ideas into much broader subject of variational analysis. And it's another subject that has been developed a lot here. We regularly at CMM have had meetings involving variational analysis, bringing people all over the world talking about it. And it's inspired by optimization, but also lots of other things, equilibrium theory and so many other things involved in it. Now, I will start to talk about optimization. I'm going to, I'm choosing relatively, I try to find, what's a good balance. I'm taking a relatively simple model, but one in which I can hang on to it, some key ideas that I want to tell you. So the idea here is that I want to minimize a function subject to linear constraints. I just have this constraint ax equal b. And I'm minimizing a function, and in my whole talk we'll assume convexity. This is a convex function, but this function could take on infinity. Now, what that means is, infinity is just a way of tagging the points that I don't like. Where the function is infinity, certainly I'm not going to want to have them. If I'm minimizing, I'm going to avoid those. So it's a way of encoding the points I don't want to allow in the optimization problem. So built into this is an implicit constraint that the points I'm involved with are the ones where the function is finite. And this simplifies a lot of notation. It's very important conceptually to do this. An example could be, because this is very, very common. I know, again, I had a classical introduction to mathematics, and one of the important things there is we should try to understand everything from a coordinate-free point of view. Coordinates are some last-minute thing you enter into a problem, and how to understand it, you introduce a basis and then change to another basis of your subspace. But in optimization, the coordinates are given in a particular way. For example, you may have a vector in which the components represent different quantities of resources, coal, oil, or something like that. The coordinates are critical, and the partial order given by the coordinates is critical in a lot of things. So we may very well want to minimize this subject to the variables all being non-negative, you see. So that would be built into the specification of this function f, where it's going to be plus infinity or not. So that's in the background. All right, now we get into something which is classical because it goes all the way back to Luigi Lagrangio, that you can have Lagrange multipliers for this constraint. Then you get what is called Lagrangian function. And now under my circumstances here, for any fixed choice of the multiplier vector, I will have a convex function in x. And on the other hand, of course, it's just going to be linear, or I prefer to say affine because it doesn't vanish at zero, affine function of the variable y. In more general optimization, we would have inequality constraints, much other kind of constraints, and it would be more complicated, but this solves the picture. So now then there's this question of how you characterize optimality. And here's where this fascinating element comes in that so inspired me from the beginning of my career, that somehow optimality brings out a zero-sum game. How could this be? So I won't go through how we get this, but it's all pretty elementary. And you need some kind of condition to make sure that something is degenerate, but it's all pretty minor here, but I don't want to bother to explain it. But roughly then, after you pay a very tiny admission fee, you get this theorem, which is that a point x bar solves this given problem if and only if there is a multiplier vector that provides a saddle point of the Lagrangian in a minimax sense. And I write it here with argmin. Argmin means the thing that gives the minimum. Argmax, the thing that gives the maximum. So in the first of the argmin you see there, if you, So if you fix the y, then you have that this minimizes this. On the other hand, if you fix the x, it maximizes this. This is exactly the kind of condition that gives you an equilibrium in a two-person zero-sum game. One player is trying to minimize, the other one wants to maximize, and they fight it out, and they reach an equilibrium this way. So, but that means that also, this is part of this whole game setup, that the other vectors solve another optimization problem, the strategy problem for your opponent, the dual player. And here this is expressed by something which I like to, because I want to point out that we can dualize these convex functions. In physics, there's something called the Legendre transform, which dualizes functions. It's very important in passing through the calculus of variations, but it was very poorly organized and expressed in classical mathematics. They don't pay much attention to what the domain is, to what extent the definition can be carried out. But we have an optimization now, the Legendre-Fenchel transform, which dualizes convex functions in a beautiful way. So here's a dual problem in which you have here the transpose matrix or adjoint operator, however you want to look at it, and this. And by the way, this dot means inner product. I'm dealing with spaces like Rn. So they're Euclidean spaces, but I'm not happy about coordinate free. I like my coordinates in optimization in general. So this is a background because all these things will be critical. So it seems, you see, one of the weird consequences of this is that you just think you want to solve this problem P, but you can't solve it without solving the dual problem. Somehow you have to take into account that there's an opponent with a dual problem. And then that's going to influence your methods of solution. The whole idea is this isn't anything like typical methods of solving problems in classical numerical analysis. Is something really different. Now I'll get to the meat of what's more challenging. Optimization, as I say, it started out with the advent of computers. Then it went through a long phase of development, and it developed very good methods for solving highly nonlinear problems, but of a relatively small dimension. And then the subject was there was still a lot of theory going on, but in some ways the subject was not as active anymore. Then came across a new kind of computer revolution in terms of machine learning, and it became extremely important to solve problems that were huge, connected with machine learning and data analysis and training things for face recognition, all this kind of huge computer stuff. And so it got into, again, there could be inequality conditions, but equation constraints are very important there. And the whole point is, though, that there is special structure. Now, let me explain the structure. Basically, where I had a single matrix before, I want to now think of a matrix of submatrices. We call this block structure. A matrix has, I have rows and columns of matrices. And then I want to think that the thing I want to minimize here, this F is, okay, here, let's just get down to basics here. So where I had this vector X, now I have these components, but these aren't numbers. They could be numbers, but in general, these are themselves vectors. So I have vector xj in a space of some dimension. Dimensions can be different. So then, and there could be a bunch of those, and those dimensions add up to, of course, to the whole dimension. And then I have the thing I want to minimize divides up equal. This is critical because I want to be able to take advantage of this separability. And each of these is supposed to be a convex function closed. In other words, lower semi-continuous. Its epigraph should be a closed convex set. And then over here, similarly, I want to imagine that this is divided up. This is a vector with subvectors, and these subvectors belong to spaces of various dimensions. So I have all these blocks, and these are forming a supermatrix in a sense. It's a matrix of blocks, which each block is a matrix. But here's the critical thing for much of this modern subject. Most of the blocks are null. Relatively few blocks are non-zero. So every row and column must have at least a couple because they're supposed to link things together. Now, there could be a lot of other conditions, but the other conditions are all built into where these functions are infinity or not. These are like the separate conditions, separate constraints, like maybe xj has to be non-negative coordinates. So that's all built into this function. But these are the things that connect or they couple all the things together. And so then how can you make use of that? And I'm going to explain it in terms of economic ideas that can inspire what you might do here. So we have, and then now here's the thing too. These problems are enormous. It's just hard to imagine how big a problem that people are able to solve these days. How about 1 billion variables? Can you imagine this? This is a completely different scale of something. So you can't waste time. Now the idea here is that we imagine in the background that for each of these indices j, each component, there is in the background a problem that's independent. I just want to minimize, I'm operator j. I just want to minimize my function fj. And the constraints are built into where this function is infinity. But I'm stuck. I can't do it myself because I need resources. Resources coming from the outside, but other operators j also need resources, and we have to share them. We're maybe competing for resources. Now, if only we can somehow figure out about these resources, we could go back to solving problems independently. So that's kind of the key here. So there are shared constraints, and these are different kinds. Like one might be, economics. One might be labor type constraints. Another could be certain resources, or there are different kinds of constraints. That's why we have the division up of this side too. And but maybe there's some way anyway to bring it back, reconfigure this so we could get back. And that would be then the key, that you could have computers, to put it back in the computer side, different processors could independently, in parallel, be solving various, even the subproblems could be large, but they would be much smaller than 1 billion, let's say. So now I'm going to discuss a couple ways that you could look at this from an economic point of view. So as I say, let's imagine that the resources have to do, it could be much more complicated. There's so many other things we could discuss here, but this is really good to just get your thinking going on it. But those are resources. And they're available only suppliers, only so much money. They have to share the same budget for same source of money. There's only one funding organization, and there's only one group of personnel or vehicles or whatever it is. Although we always I want to talk about continuous optimization and not discrete optimization. If numbers are large enough, people will model everything with continuous variables anyway. So now I want to think of that the indices I there for those shared constraints stand for different kinds of resources and these supplies, and then the vector bi, the coordinates of it give how much crude oil, how much soft oil, or different kinds of oil. That's the supplies. And then for each of those, there's going to be a coordinator. And on the other hand, for each of these j things is something that's consuming resources, an operator. So now I'm going to describe two ideas that you recognize as age-old and to some extent political. In fact, in the days of the Soviet Union, it was sort of difficult for people over there to discuss optimization in the same way, because everything seemed to have a political overtone to it. So, here's one way, which you could imagine was more congenial in the Soviet Union. you have a coordinator simply decides how much each unit, each independent operator should have. The coordinator chooses vectors that add up. So these supplies in this vector are shared between these operators, j equal 1 up to q, and vectors that add up to that. And then the coordinator simply tells each operator, this is what you've got to work with. Okay, then the operator knows this is how much of type resource I for each I, so then the operator can go back to minimizing that function subject to knowing how much resource it has. So this would be one way. Now that would be to solve, each operator would solve a problem, and there would be a minimum value in that problem, which would be this. But of course, this is like a subproblem. You still are left with this issue. Well, then what do? You still have to figure out what would be the best. Well, maybe in the Soviet Union they didn't get as far as that. But anyway, from our point of view, we have an overall optimization problem. So then we're still stuck with figuring out how you would, what choice of sharing would minimize this sum. But actually there are a lot of methodology in what we call linear programming and mathematics that worked with this kind of thing, figure out how to do that. That was called Bender's decomposition, one kind of optimization that you could do with that. All right, now here's another idea, which obviously has different kind of political overtones. You're going to use markets to do the trick. Markets will take care of everything. So according to this idea, the coordinator for resources of type I assigns a price vector for those resources. And just transmit that price vector to the operator. Then the operator will minimize, so this, if operator J chooses decision xj, then this matrix converts that into how many resources of type I that decision used, and then we multiply it by the price. Then this is like the cost of all those resources. We're adding up all that cost. I'm assuming, I guess here, that this is measured in cost terms too. So then you're just going to do that. So what's implicit in this is that operator, it's as if the operator can buy and sell these resources, like there's a market in the background for buying and selling these resources. And then the operator can just optimize independently according to what the market is saying. And so you have a decentralization by market. This, of course, we hear a lot in politics about how markets are supposed to perfectly decentralize and make everything optimization. Okay, but this sounds far-fetched. That's so magical. How could there be any prices that would do that? The idea is, if you could just get the right prices, then when the agents optimize just independently, somehow by magic, the overall problem would be solved. The problem of the whole society would be solved by independent, greedy actions of the individuals. You can see where the classical economic theory is coming into this. Well, there are such prices. There are, because these prices are exactly the solution to the dual problem in here. Your opponent here is the market, which is trying to make the prices be as most disadvantageous for you as possible, but in that sense somehow identifying the true values of these resources. So there are such things. So you could solve the dual problem. Well, but how are you going to do that? That's another problem. Is that any easier or harder than the original one? It's probably a smaller dimension. Remember, we have something m times n. M is somehow the number of resources. N is a number of decision variables. And usually there's much more, the number of, the n is much bigger than the m usually. So this would be a smaller problem. Anyway, there are ideas about that, and this will come in eventually. But now we're going to skip over to, let's see, do I have this yet? No. Oh, I got too far away. Wait a second here. Okay, now we're going to get into a real algorithm in which, this is something which, I've worked for years on decomposition algorithms, but this particular one is one that I've just been working on in recent months. It's based on some things I did for the last few years. But this kind of specialization, because I last week I was visiting longtime colleagues at Hong Kong Polytechnic University, and they were stressing to me how all this stuff about sparsity. So remember, the idea is, well, let's go back there for a minute. In each of these cases, we imagine that, again, that this is going to be sparse, so that a given operator may only use certain kinds of resources. So there are various links here, but we have to figure out how we might solve this without activating more variables than we would really need. All right, now here, this is what's interesting about this is, although this is derived in a technical way, I don't know if I get a chance to really explain anything about that. It somehow in here are reflected all those ideas plus more. There's a third idea which is coming in here, which I don't have time to explain, but it also has a very simple background to it, which is that we add in this, when we do things, we add what are called proximal terms. This word proximal, by the way, goes back to Jean-Jacques Moreau, a mathematician in Montpellier in France, who was actually in mechanics, but became very interested in convex analysis. And he had proximal operators. And the proximal is basically a word saying, try to not get too far at one time from where you have been already. Anyway, we have proximal terms we add in here that stabilize and then get you good convergence properties. So, all right, so here's the idea. Now you see this is going to be like something working economically in a sense, but now instead of factories and suppliers or something, we have processors of different kinds. Think of them as like computers that can act in parallel. So the operators, all they know is they have a current decision that they have gotten to so far, but they're going to change it. They want to improve maybe. So they have a vector, K is the iteration. I'm just describing the general iteration here. Each operator J has a current vector. This is only stored, that's only, at the very end, all those operators can report what the solution will be that you get. But at a given time in all of this, operator J just only has that vector. And now operator J gets from the coordinator these allocations, Bk, Ij. But, I forgot it and left it out here. Also gets, it should be not just those, also gets a price vector, Yi. Oh, this is also a mistake. This should be Yik. Also gets these and gets a Yik, a current price vector, Yk. So both of those ideas, prices and shares, are entering into this. Then this operator J will minimize this function plus, now this is familiar, this is this thing about the cost at those prices, except this should be with Yk, the current price vector. And then like as if they could be bought and sold. And now here are two terms where we have the norm, Euclidean norm here, squared with, these are parameters R and S. This one tries to keep your new decision near the one you have so far, not let it stray too far. And this is something like a penalty on this. This should equal, what you now do should equal what you've been given as your shares, but you don't have to exactly equal. There's a penalty attached. So you come up with this, and then what this operator does is communicates doesn't communicate this decision, only communicates to coordinator I the resources that were used in that decision. Communicates that to each of those coordinators. Then those coordinators just do something rather separate. They look at here, coordinator I looks at these resources I, and here was the original amount, and here's the current amount that those decision makers, only the coordinator knows what they've done. The other operators don't know what each other are doing. They're all independent. And this coordinator sees this is what all the resources that those operators want, and here's the amount there. So this difference is the discrepancy. Might be some too much in some coordinates, not enough in some other coordinates, or not equal. All right, whatever it is, divide that by this. This is the number. Here we're getting into sparsity. We're only looking at, for supplies I, We're only looking at the operators, J, that actually use those supplies. Maybe out of a billion, there are only 10 operators that use those supplies or something like that. So we just divide this equally. Remember, some components are positive, some that's for this vector. All right, now this is what they wanted. Now you just add that on there, and that's the new supply, the new shares. And then you update the multiplier vector, and here this penalty parameter comes in. Okay, then the coordinator transmit those back to the operator, and the operators go again. So let's go back and forth. And the only thing, the coordinate operators only store those vectors, and the coordinators only store the y. They don't store these v vectors. See, they don't need to. They only store those y vectors. And so it goes back and forth. So what happens when you do all of this? They can act in parallel, and they only have to communicate. Oops. They only have to communicate. Something's wrong. All right. What the heck? Okay, okay. Keep my fingers away. All right. They only have to communicate in the pairs that are not null. So only minimal amount of communication. Okay, then what are the mathematical properties? You can start anywhere and will always converge to a particular solution. And in a certain generic sense, it's going to always be at a linear rate, although you can't necessarily control it. And there are other well-known procedures, very famous, one called ADMM, alternating direction of minimums. By the way, invented in France. It's ADMM. But it doesn't really address sparsity, and it has much more complicated theory of convergence, which is harder to work with. It's more opaque. This goes back to basics, and anyway, it's based on things that I've done recently. So I wanted to say a few words about how this comes from something much more general, which is where I got into this with trying to do something really basic in optimization, and not just optimization. This also applies to variational inequalities. Another subject, by the way, highly developed in France, which then became important in optimization itself. Variation. Pierre-Louis Lyons was one of those most active in this idea of a variational inequality. They did it in PDE type territory, but it also has importance in everywhere, equilibrium issues. So, but I'll just describe optimization version, which seems kind of simple. You want to minimize a closed convex function over a subspace. Well, maybe you want to minimize over a lot of others, but it's important here to have just a subspace, because a subspace is going to be viewed as giving linkages between things. And what you would like to do is remove these linkages, because then the problem would be simpler. So it's kind of like what I was describing with linkages before. It was kind of between the different agents that couldn't act independently. So imagine for a moment that this is just a differentiable function you wanted to minimize over a subspace. Then, of course, the optimality condition would be that the gradient would be orthogonal to the subspace at the minimum point. Well, the analogy in convex analysis is we have subgradients. And you see here, instead of saying that, here I have this V bar is a subgradient at U bar. It could be a special case, V bar is the gradient, because if there's a single subgradient, it's actually the gradient. But in general, it's a subgradient, and the subgradient should be an orthogonal space here. But what that means in convex analysis, this condition, orthogonal, is that if you were to take this function phi and subtract it, tilt it by subtracting this linear function, then you would have U bar in that. So here you see another thing, which is a kind of truism in all of this optimization theory. Once you can understand the conditions for optimality and how to look at them in one way or another, that will give you a clue for developing a numerical method. So the idea here is, if you magically knew what this was, you could minimize. Look, this isn't minimization over a subspace. This is minimizing over the whole space. If I only knew this vector, then I could get the solution I want to this problem by minimizing this over the whole space. Well, there could be a small bug in here, because what if there's more than one thing giving the minimum? All I know is one of them could be. So that's where we may need some stabilization. Proximal things will come into this. But the idea is that this decouples these linkages, if you could know that. All right, now you make it into an algorithm. You're going to minimize where these are going to change from one iteration to another. And then I'm going to add some proximal terms so I don't get too far away. This is going to also make a unique minimum at every point because of convexity. I'll have strong convexity. And then what I want are these pairs are to converge. Well, that could be wishful thinking, but it's not, because we know how to do that. Turns out that we identify the whole space as this product space. Now here's a case where, in a sense, the coordinates really are changing, because now I'm decomposing the space as this product of S and its orthogonal complement. And then I take a partial conjugate, Legendre-Fenchel conjugate of this function phi in one of those, and then I use something very basic called the proximal point algorithm to find a saddle point. Again, here we have the game coming back in there. This is a minimax saddle point in this obscure way, which is coming in there. All right, and then out of time, I don't want to do that. I just wanted to give you the flavor of all that. Then you have an algorithm in which, in one step, you'll do some minimizations, in which you see here both of those things happening. Here I have this tilt vector, and I have a proximal term, and I have some more general things, because I can change the geometry around. It's more parameters, and then I do some projections, and that's all you do. And then again, I get all those things, and then we even know how to extend that locally, even to non-convex optimization. So I hope those ideas gave you some flavor of how the subject works, how closely connected it is with economics, and why it's different. These are just in case somebody wanted to follow up. These are papers of mine, some of them quite recent, as you see, which deal with this subject. All right, that's all my talk. Thank you.
Thank you very much, Terry, for your wonderful talk. Then now we have time for some couple of questions from the audience. I have one question, but I prefer to start first with your. Do you have a comment or question? Yes.
You mentioned mainly economics example, right? Motivation, but also you mentioned quickly data and machine learning, right? So in those cases, what are the bottleneck or the main difficulties that you find with this approach, or I don't know, what is the special for those cases?
Well, a lot of them have a statistical origin, like you have some huge set of data where you're trying to identify, so you consider some disease. Does this person have breast cancer or something? So you have like a vector of 29 coordinates that measure something about the blood, something about the shape of something that was seen. So I have this vector, and then they're trying to, for example, separate by some, and you think of that as a point in a 29-dimensional space, and then you're trying, and then you have, a million of these points, and you're trying to see, like, set up a hyperplane that best separates the one from the other, so you can see how you get a very large thing. And then they have to introduce something called a loss function, which is not necessarily symmetric, which would kind of measure how you regard the relationship of a particular data point to this hyperplane. And your variables are the parameters that will give you the hyperplane, the coordinates that will determine the hyperplane. So you're trying to find this in a high space, but then, as I say, the problem is you have all those data points. But this is a typical type of problem of machine learning, and there are many, many different ways that, and often those expressions that you use as a loss function have a kind of a max in them, which max of two quantities, which make them be non-differentiable at that corner point. And But all this can easily be handled now, and it gets also into the theory of risk, which is something I've worked on a lot. Yeah.
Thank you. And then I have a one question concerning the convergence result, because
Yes.
you propose an algorithm. What about the convergence result?
Yeah. So where do those convergence results come from? They come from this fundamental thing which I got involved with back in the 1970s. It's sort of interesting because I spent, again, here's my connection with France coming back. I spent the academic year 1973 to 74 in Grenoble. And while I was in Grenoble, I met somebody who was working on a kind of method, and I was already interested in something called a maximal monotone mapping, which is something like a nonlinear generalization of a positive semi-definite or positive definite operator. It's not, and I knew something about that. And then it turned out there was some problem to solve to try to find a zero of such a thing, and they had some inefficient kind of algorithms for doing that. And I realized that there's something better that could be done. So I got into writing this all up as proximal point algorithm. And basically it's an algorithm which has an interesting property that no matter where you start, you will converge to a particular solution, even though there could be more than one solution. It's interesting, and I've since worked harder on that to refine exactly how that would work. But that goes back to something I wrote, and you know, I've written many things, and as Alejandro says, I have some books that are extremely highly cited. But if you look at papers, this is among the top 5 or so papers in my career of hundreds of papers that were cited, that property. And I'm still interested in that idea today. And all these other things, this ADMM, that's the main kind of competitor, all these things go back to the same algorithm, basically, the proximal point algorithm, with proximal again coming from Jean-Jacques Moreau. So France is very much involved in this in the background, interestingly, isn't it? Yeah.
Thank you. And okay, any other comment, question? Yes?
Hi, when you optimize the difference between the nonlinear function and the linear function, why don't you change the variables to the UV? Why don't you change the variables?
Well, the variables are kind of fixed. I'm not sure why would I change the variables. I have the coordinates of the are already fixed, like they represent coal and oil. I have no particular incentive, and I might have non-negativity constraints, so it doesn't help me to change the variables. So non-negativity constraints, if you change the variables, would turn into much more complicated inequalities. So we usually don't do that, but what we can do sometimes when we have these quadratic terms is introduce preconditioners that simplify them or take advantage of some like Hessian structure, second order structure. We could do that.
Another question there. Axel?
Thank you very much. Could you give more details about the non-convex case, the application of this
well,
method?
yes, I didn't prepare this on a slide, and the slide is gone. But the basic idea, as I say, it goes back again to this proximal point algorithm, that the proximal point algorithm depends on a maximal monotone operator. But then what came to light is that the whole thing is really local. You don't need this global maximal monotonicity, only local maximum monotonicity. And then everything will work. So then I started exploring that, I don't know, 7 years ago, 6, 7 years ago. What does it mean, say, for a function that's not necessarily convex? It has a subgradient mapping. We know how to deal with that. We're non-convex. What if that is locally maximal monotone? We know that if the subgradient mapping of a general function is actually monotone, then the function has to be convex. But what if it's just locally, in the primal dual, locally convex? And it turns out that that's something that deserves to be called variational convexity. It's not the same as local convexity. So anyway, you can propagate that all through here into what now turns out to be maybe the best concept of a second order optimality condition. It generalizes everything we know in good cases about what second-order optimality conditions should be, something that involves variational convexity. And what it means at the heart is that you have this local monotonicity. So that means that you could actually, once you get close enough to such a point, in the primal dual sense, remember these things are always working with both primal vectors and dual vectors. So if we could only get close enough, then even though it's a very nonlinear problem, the whole thing will work. Even the decomposition will work. But the real trouble is we don't know how to get close enough. This is a big issue. How do you get close enough in the first place? This is not so easy, but maybe there'll be some answer to that.
Okay, then thank you very much, Terry, for your talk, wonderful talk, and then say again, thank you. Now a break? Now we have a break, right? A coffee break, and then drink coffee.
Sorry again. So now for the second part of the morning, we have I think it's the data and probability session. And it's a pleasure to have Ozgur Yilmaz for the first talk. Ozgur is a professor at UBC, at the University of British Columbia. And he's also the director of the Pacific Institute for Math Science, PIMS. We have heard a little bit about that and what PIMS does earlier in the week. But in terms of research, his research focuses on applied and computational harmonic analysis, information theory, compressed sensing, and signal processing. Ozgur has made many very important contributions to the field, and I think it has been sort of moving maybe lately a little bit closer to, I guess, machine learning or data science, and we're going to hear a little bit about that today. So the floor is yours.
Thank you. Thank you very much. Well, thanks everyone. Thank you first of all to everybody involved with this amazing gathering at CMM, the celebration of the 25th anniversary of CMM. It's my first time in Santiago, and I've enjoyed every minute of it. It's also been very productive in creating new collaborations and so on. And I'm very happy that I'll talk about math today. My talk is on using deep learning in compressed sensing. I try to make it as non-technical as possible, and I want to explain what the main contribution here is. This is not a talk about mathematical foundations of deep learning. It is rather using deep learning as a mathematical tool to perform certain tasks better. This is a list of the contributors to everything I say in this talk. Some of them are former students, current students, and colleagues at UBC. Let me just go into the problem. The problem is I'm going to talk a little bit about the general framework about inverse problems. The idea is that we have a signal x naught, and we would like to kind of learn about this signal. And what we have is the observations of the signal under some forward operator, curly A, that are contaminated by additive noise. And what we want to do is estimate or recover x naught. Sometimes we can do exact recovery if there is no noise. Sometimes we will want to estimate it with certain error guarantees and so on and so forth. So this is the general problem. The typical issues, challenges are these problems are often ill-posed. There are infinitely many solutions, or there are no solutions, but there are approximate solutions, which again are infinitely many depending on the criteria you want to impose. And finding them is hard. What we need is a tractable and numerically stable method that gives us meaningful solutions to this problem. And the typical way to do this is impose a model on the signal and restrict the solution set. And that model better represents signals that really are the type of signals you want to find. For example, it could be speech signals, it could be images, it could be some specific class of signals, and you want to model that signal class and use that in restricting your options when you consider this problem. Okay, some examples here from the type of literature I'm coming from. Inverse problems is a huge area, and I'm going to be looking at the type of problems that relate to what I've been doing over the last 20-something years. And the examples are imaging, medical seismic, image restoration, and in painting, denoising certain types of signals. And a specific example is compressed sensing. I'll come back to compressed sensing. I'll talk a little bit about this. This is a paradigm of signal acquisition that was made popular that was introduced actually around 2005. And it's become exceedingly popular. The original papers are by David Donahoe and also by Emmanuel Candez and Terry Tao, and these papers have received on the order of 30,000 citations in these last 15-20 years. Okay, so this is our focus, and what I want to do, just let me say that, is use deep learning for this aspect of inverse problems. I'm going to use what we learn from using techniques in deep learning to model signal classes, and then in a mathematically rigorous way, incorporate that into solving the problem. As I said, I come from this school, and there's this seminal paper that Ingrid Doveschi, David Donahoe, Martin Wetterli, and Ron DeVore wrote in 1998. This is incidentally 1 year after I started my PhD. And they listed 3 grand challenges of data compression in this paper. And these are obtaining accurate models of naturally occurring sources of data, like natural images, obtaining optimal representations for such models, and rapidly computing such representations. This is the time when wavelets were kind of very popular, recently introduced. And the reason for that was essentially they provide almost optimal representations in an ad hoc way, by the way, for images, and good models of naturally occurring sources of data. In particular, one used, I'm going to talk about this now, but there was this understanding that signals of specific types can be approximated by function spaces of certain smoothness levels, like certain Sobolev spaces or Besov spaces, and then you could use properties of these function spaces to construct compression algorithms or denoising algorithms and things like that. What I want to say is these 3 grand challenges apply also to inverse problems, at least the ones that I'm going to be looking at, and I'm going to kind of go over them a little bit. The idea that you have to model a naturally occurring set of signals requires you to develop approaches of making reasonable, meaningful models. And there still are 2 main approaches. The first one I'm going to call the deterministic approach. And here, the approach is to take your signal, and you assume that it's in some fixed subset of some ambient space, okay? For example, you could say that my signals are in a specific k-dimensional subspace of Rn, linear model, right? So very simple model, or whatever. So some fixed, the keyword here is fixed, and then you use a generic program to obtain an approximation, which is saying that I want to look at all elements of my space, fixed space, and minimize the mismatch error. Okay, so I find the best approximant in this space. And hopefully, if this space was the right way of modeling my signal class, that's going to give me a meaningful solution. Another way of looking at this is I'm projecting onto the set that you obtain if you applied your forward map onto this model space. Okay, typical signal models. This is the set of band-limited functions. This is the classical sampling theory. This is case-sparse signals. This is behind compressed sensing. I'll come back to this. So this means that you have signals in Rn. N is very large, but only k entries are non-zero or meaningfully different from zero. You know, this means only k is non-zero, but you can also use this as an approximation. This means that the wavelet coefficients are sparse. Okay, so these are the type of models that people use, and there are thousands of papers that use these type of an approach to solve the problems, various inverse problems that I listed in the beginning. Let me give you an example here and use this opportunity to give you a brief summary of compressed sensing. So in compressed sensing, you assume that your signals are indeed k-sparse in Rn. So only 10 entries are non-zero. At most 10 entries are non-zero in 1,000 dimensions. Think of it like that. And you have a measurement matrix. This is just a matrix. M by n. M is much smaller than n. Okay? N is your ambient dimension. You say you have a 1,000 dimensional signal and you make only 100 measurements. Okay? Normally, you can't get your signal back from that many measurements, but we will use this fact that these are sparse to actually get the signal back. Okay? You take this measurement matrix, you make these measurements, you have m measurements now, much less than the ambient dimension. They are corrupted by noise, and you want to solve, that parenthesis is wrong, that's the 2 norm of the mismatch. I just wanted to emphasize the 2 norm last night, and I made a typo while doing that. Okay, so this is the 2 norm of the mismatch. You minimize that, you find the x that minimizes that, that's k-sparse. Okay? It's NP-hard in general. So you can't expect to be able to solve this problem in a tractable way for any phi, for any k, for any n. But it turns out that if you restrict the type of matrices you're going to use, and if this k is sufficiently small, that's another typo, I apologize, this is little k. Little k is sufficiently small with respect to m and n, and m is big enough for this k, but still much smaller than n. I can quantify all these, but I don't want to go into that type of detail. Then actually you can convert this problem, which is NP-hard, which is combinatorial, to a 1 norm minimization problem. You want to minimize the 1 norm subject to the mismatch is less than epsilon. If there was no error, I could say phi x equals y here. This would be an equality constraint. And this would be a linear program or a convex program, generally, quadratic program. So this is a tractable algorithm, and it turns out that when you solve this, you will be approximating your original signal within the noise level. If noise is 0, you will get exact recovery. The math is here. What are the suitable assumptions on phi, k, m, and n? You want to be able to recover, get this type of result with as small as possible m, the least number of measurements for a given sparsity level. And you want it to depend on these parameters optimally. And the optimal dependence is, let me say it in words, m should be as big as k log n. Okay? So the dependence on the ambient dimension is logarithmic. If you have a 1,000,000 dimensional signal, if it's sufficiently sparse, that only increases your complexity by logarithm of that, which is essentially 1. So this is a very strong paradigm. And the way to construct this phi, it needs to act like an isometry on sparse signals, which is called the restricted isometry property in the literature. And proving that for a given big matrix is NP-hard. So we can't actually, if you give me a big matrix, I can't check. But what I can do is, if I take a Gaussian random matrix with probability close to 1, that matrix will satisfy this property. And if I take a Bernoulli matrix, which is, again, every entry is equally probably plus minus 1, with probability as close to 1 as I want, I can make it satisfy this by picking it sufficiently large. and at the optimal dimension relation regime. So these matrices are numerous. There are a lot of them, but we can't put our hands on any one of them. There is no, to this day, which is 20 years after, there is no deterministic construction at the optimal dimension relation. The best is, I mean, you can easily, as I said, the optimal relation is M should be like K log N. What you can prove easily for existing matrices is M is square root of N, but that's too big compared to log N. And it's called the square root barrier. The best result reduces that power from 1 over 2 to 1 over 2 minus epsilon by Bourgain on a 100-page paper, and that epsilon is on the order of 10 to the minus 20 or so. So this is a hard problem, it's still open. With that, let me quickly go to leave compressed sensing and talk a little bit about the alternative approach, which is the Bayesian framework. So you still have the inverse problem in the same structure. X0 is your signal, but now you think of X0 as a realization of a random vector. And the density of this vector captures the prior information. Instead of modeling it as being in a function space, you say, here's the density, and that actually gives me information about the signal. The observations are also random variables in this model, and this denotes the posterior distribution. And then you try to find your estimate as the maximizer of this posterior. And this is called the map estimate, maximum a posteriori estimate. Using Bayes' rule, you can play with that, and you can turn it into this expression. And if you look at this, if your noise, this is basically, this comes directly from the noise, and this is the prior on this is the model. Okay, if you think about, this is the signal model and this is the noise. If you assume the noise is Gaussian, this problem changes to this problem, where you have, it's very similar expression. You need this R of X. This is your regularizer. And to get that regularizer, you need the prior distribution. And again, when you do this, the typical or classical way was to say, okay, let's now make assumptions like we did on the signal class. This time we make assumptions on the prior. And we could say, for example, the wavelet coefficients are IID Laplacian, which gives you this, then R of X reduces to the one norm of the wavelet coefficients, and that leads to an unconstrained lasso. So this is an optimization problem we know how to deal with. The other option is learn this prior from data. And this is where deep learning will come in. So I will use deep generative models that are very strong now to learn the prior of data. Okay? So this idea was first used in the context of compressed sensing in a paper in 2017. And they said, here's the summary of the idea. You have a generator network. The network, this was a GAN or something, variation autoencoder, which takes a small dimensional latent space and maps it to the signal space. And the way it's trained is that if you take Z, which is the latent code, as a Gaussian, IID Gaussian, the neural network maps this to an entry in the signal class. Okay, so in other words, the PX, the learned prior, is the push forward distribution of PZ under this map G. Okay, this is what the generative models do when they learn. This is the way they learn. And that means that you can actually sample the distribution, the sampled from the signal space using these by sampling from the latent space. Okay, so this is how you generate a face that nobody has ever seen before. You pick, this is the face space, like the space of faces of people. Okay, I don't know the prior distribution, but the model learned it. And now I want to take a random face, which doesn't belong to anyone. what I do is I take a random Gaussian vector here and I apply G to it, and that creates the random phase. Okay? So this is the general mechanism the variation autoencoders or GANs work. And this allows me to sample the signal space or to model the signal space in a way actually that's much better than the old models, where if I say all natural images are in this Besov space, obviously not every function in that Besov space corresponds to a face or image. Whereas here, I can actually create images that are of interest to me by just picking a random vector and applying the neural net. Okay. So how do we use this in the, let's say, compressed sensing framework? So we have the measurements. This is basically, this is my noise, okay? This is the compressed sensing matrix, and you want to solve this problem where, again, this is the two-norm mismatch, and this is negative log prior. I don't know what the prior is. I know that I can sample from it, okay? So I know that the signal model is imposed by the generative model, but I don't have an expression for this, so I still have some work to do, okay? What I do is I kind of make a crude assumption. I say that forget about the distribution there. Let's say that my signals are modeled by the range of this network. Okay, anything in the range is in the signal space, and therefore I'm going to use an infinite valued function here to take this out of an option. My regularizer will be imposing that I find a solution that's in the range of G. And that corresponds to this problem, which is saying, again, look at all x's in the range of the network and try to find the best that minimizes this expression. And then you can go back to the signal. This is going to solve it in the latent space and here, and then you go to the expression. This is the solution, the approximation I get using this generative prior. We focus on a fully connected generative neural network in this work. This can be adjusted. It's not really, but it makes things much easier to deal with. And I'm going to also assume that my original layer is k dimensional, and the output is n is the signal dimension. The activations are ReLU. This is this function that it's zero if its input is negative, and it's equal to its input if its input is positive. And with that model, I'm going to do compressed sensing in the way that I described, and my observations are given by this, or you can add noise. Actually, that's not that's just for simplicity here. I wrote it this way, and you recover using the optimization. So by solving the optimization problem I posed with G as the generative model, and we want recovery guarantees, and we want algorithms, and we want to be able to have these for a broad class of compressive measurement matrices. So compressed sensing, when it came out, as I said, we can't prove anything concrete for any given fixed matrix. So the probabilistic results work for Gaussian matrices, sub-Gaussian matrices also, and for Bernoulli matrices. That's not really ideal, because those are matrices that you have to store in memory. And when you have real signals with millions of dimensions, those matrices you can't really store, you can't apply fast, and so on and so forth. So one immediate push has been after that to generalize this to Fourier-like matrices. If you can do this with discrete Fourier transform type matrices, then things will be much more convenient, much faster. And there's literature in the classical compressed sensing that shows that you can work with randomly subsampled Fourier matrices, which can be implemented matrix free and don't need to be stored, and so on and so forth. This literature did not have that because it poses kind of technical difficulties to to work with phi that's not Gaussian or sub-Gaussian, and our contribution has been to generalize this. And here is the summary of what our contribution is. So the main focus has been Gaussian and sub-Gaussian and exact recovery guarantees. So this is when phi is sub-Gaussian and the underlying generative model has suitable weights. And this is another thing. Now, compressed sensing is based on modeling the signals and then use that model in proving the guarantees. When you pass to these deep generative models, algorithmically everything is great. So I have a model, I can apply that model and I can solve. But to prove recovery guarantees, I need to use properties of those functions underlying that model. Okay? And what people have done in the earlier works to kind of deal with that is they assumed, oh, let me assume that my generative model, every weight is random, Gaussian. Of course, this is a very unrealistic assumption because the model is learned, it's fixed, it's not random at all. And we wanted to kind of remove this requirement and be able to describe this function in a way that depends on the actual network that we have. And so we found a parameter. We are looking at compressed sensing matrices that are subsampled unitary matrices. F can be, for example, the DFT matrix. We introduce the coherence of a generative model. So we don't make any assumptions about the weights being random or anything like that. We say, give me a deep generative model. I will define a quantity called its coherence with respect to the matrix that I have here. And then this coherence will be used to establish guarantees. Everything will be in terms of this coherence. And we do not make any assumptions on the weights of the fully connected DGM. And we want to establish effective sampling strategies. And I'll say a few words about that. How much time do I have?
10 more minutes.
Okay. I'll say a few words about that. And we will provide recovery guarantees and algorithms, though this is not the focus today. I'm going to focus on the recovery guarantees for this setting. Okay, so coherence. Again, one thing in compressed sensing that's important is when you are taking measurements with a matrix. Let me go back actually one slide. So in fact, one more slide. So you are taking measurements here. Think of this phi as a short matrix, okay? And so it's going to have a big null space. Yeah. If x0 solves this equation, x0 plus any vector in the null space will solve this equation too. Yeah. So any algorithm that I use that claims that it's going to recover x0 should not be interested in anything in the null space. It should not add any vectors to it. And that, if you look at the way I do it in compressed sensing, I'm imposing sparsity on the solution. So what that means is I don't want any sparse vector in the null space. If the null space has sparse vectors, okay, then that could be added to this x naught and get me to the wrong solution. So I want a matrix phi whose null space only contains flat vectors. You don't want sparse vectors in the null space. This is called the null space property. You can quantify this. And one way of thinking about it is also, if you have two solutions, phi x0 and phi x1 equal to y, phi x0 minus x1, so if you take chords in your solution space, they should not be in the null space. Okay, that you don't want sparse vectors in your null space. So that induces a notion of coherence. You don't want the vectors in your the rows of your matrix to be aligned with chords in your solution space. Okay, if you have two solutions, two feasible signals, okay, their difference should not be in the null space, should not be correlated with one of the measurement vectors. And this is now what we're doing here. We are generalizing this idea, which was explored really nicely for sparse signals, to vectors. Our model is not sparse signals. Our model is vectors in the range of a given network. Okay? It's a way more complicated object. And so we define this if you take a cone and if you take a vector in a complex vector in general, its coherence with respect to this cone is this quantity. So what's the maximum inner product? You'd normalize, of course, elements in the cone. This is the technical. You have to extend the cone, but that's not important. And then this is the vector of local coherences of a unitary matrix. So when I give you a matrix F, you compute the local coherence of each row and then put it as a vector. This is that. And then the maximum, the infinity norm of that vector is the maximum coherence of this matrix. So this is one way of, this is very similar to, parallel to what we do in sparse case. Okay? And when we do this, you indeed, as I was saying, if you have two signals, if you apply phi to their difference, you want that to be large, and that's what happens. You can bound that from the below by this quantity. So you want alpha to be as close to 0 as possible here. Okay, so you want this big. And it turns out that, as I said, given the time constraint, and I'm just going to now tell you what we can prove. We have exactly the setting I described. S is your sampling matrix. This is going to now randomly pick rows uniformly at random, okay, with replacement. I might pick the same row multiple times. It's just every row has equal likelihood of being selected, equal probability of being selected. And then if we take the number of measurements sufficiently large, that depends on this coherence. This is the maximum value of that, the infinity norm of that vector. Then we get a solution that solves this approximately. This is what we want to solve. And let's say I have an approximate solution that reaches epsilon close to the optimal solution. Then with high probability, I have this error estimate, which is the original signal and the estimated signal. The difference has the two norm bounded by model mismatch. This is also dependent on the model mismatch. This is noise, and this is the error that I make by solving this optimization problem. I mean, this depends on whether my generator network is good. So if a computer scientist manages to train a really good network, then I'm not worried about this part. Okay, this depends on how well I can approximate this, solve the optimization problem, and this is the noise level. So and by the way, we can prove that, for example, if you had a deep generative model with random Gaussian weights, like it's done in the literature, then your sample complexity is like this. Because you can show that the coherence is on the order of square root of kd over n. So this n disappears from here, okay? So the number of samples that you need to take does not depend on the large dimension of the signal, just similar to compressed sensing. And points here is, if you have a perfect model, then your error reduces to this. If you can find the global minimizer, then epsilon disappears. And if there's no noise, then you get exact recovery. So we have exact recovery if everything is under control. And there's some remarks on the proof. There's a number of technical hurdles you have to go through. And I think I don't want to spend time on this because I have a few minutes, I think, and I want to get to the end of this. Again, here I want to now get to the next sampling scheme, which is one slide. It's not a lot of things, but the idea is, if you look at what we have there, everything dependent on the infinity norm of alpha. And when f is optimally incoherent with respect to our range, then this bound is good. This is when your weights are IID Gaussian. But if certain rows of f are well aligned with, because here, if you look at the infinity norm, this is kd over n. So this, it decreases as n increases, and therefore it cancels this n when you put it in the formula, okay? But if certain rows of f are well aligned with the range, then actually this is order 1. There's no dependence on n, and then we're toast. It's not good, okay? So we have to change the way we sample if we want something that works better when this happens, which does happen, for example, if you work with MRI images, or if you work with natural images with Fourier. And so we change the way we sample. Now we choose each row not equally probable, but the probability depends on the coherence of that particular row. And this will give us a non-uniform sampling theory for this. And it turns out that when you do that, you also need to precondition with some matrix to get the RIP. This is important to be able to use compressed sensing machinery. But when you do that, you replace your complexity. Instead of the infinity norm times n, now we have the 2 norm. And this gives us an improvement of this type, which of course is very important if certain rows of f are well aligned with G. Let me finish with a couple of numerical experiments. This is reconstruction error. This is uniform sampling. This is the adapted sampling. One thing both of these show is generally this method works. So at some point here, my error is really small. The adapted one works much earlier. If you look at the difference, that's about 100 times less samples you need to get the same level of error when you adapt your samples. And here is actually an example of actual implementation of this. These are the original images, okay? And we start, this is the number of samples we pick. This is 0.002% of the ambient dimension of the signal, goes all the way to 25. The top row is the uniform. Everything is equally likely to be sampled from the Fourier matrix. And the bottom row is the adapted one that we came up. I mean, we came up with both, but this is the cool one. And as you can see, here you get essentially nonsensical results up to here, even this one. Whereas this one kind of gets to the right result around here. That's the big difference, 0.02% versus 6.2% of the ambient dimension. Same thing can be observed in the other one. It's even worse, actually, in some way. So let me finish by saying that this is one example where the current work in deep learning can be taken and used to actually solve problems we've been trying to work on, or we've been working on for a long time, and get better results. This is definitely not trying to understand the foundations of machine learning, but I think we have to do all of these at the same time. This is a big literature that's being kind of developed very fast, and it gives us opportunities to do rigorous mathematics, assuming that they do what they claim they do. Okay? All the results here are rigorous. The quality has that mismatch term, x0 perp. That is their job, that they need to make that as small as possible for us. Okay, with that, I finish.
Can you? Yes. So we have time maybe for a couple of questions. Joaquin?
Thank you very much. Very interesting talk. This is also, it could be also useful to do just standard, I would say, posterior sampling Bayesian. For instance, if you want to fill complete an image, or provide a set of possible, confidence set, let's say.
Absolutely, absolutely. I mean, the analysis is very different depending on what you use it for, but yes, it can be the basic framework can be used for that. Yeah.
Thank you.
Any other questions from the audience? Alejandro?
Just a small question. When you adapt the sampling, right? Have you tried to adapt the sampling also when you iterate in the optimization algorithm, in the sense that you increase the number of sampling when you move forward in the algorithm?
That is a good question. It was not something we did in this work, but definitely. I mean, we just used gradient descent in a naive way to solve the optimization problems. But yes, I'm sure that's a good thing to try.
Thank you.
Thank you.
Okay, so I think it's a good time to thank the speaker again. And we're gonna get set up for the next talk. So it's a pleasure to introduce our next speaker, Gonzalo Ruz, he's a professor at Universidad Adolfo Ibáñez, which is part of the network of CMM, and Gonzalo is an associate researcher or investigator, I don't know what's the right name at CMM. He's an expert in machine learning and data science, I guess both on sort of more theoretical and applied sides.
Yeah.
So I think that's a little bit about what we're going to learn about today.
Okay, so thank you very much, Daniel, and thank you very much to the organizers of this event. Yeah, so my talk is going to be more on the applied side. So I didn't put any formulas or equations, but I think it will be interesting anyway. So this is basically applications of AI for Alzheimer's disease detection. And the idea here is to show some of the architectures we've been developing using convolutional neural networks and also vision transformers, and combining both approaches as well. There. So basically, to point out, so the work I'll be presenting is part of a project called Anillo project, which is an associative research project from the National Agency of Research and Development here in Chile. And then I'll give a brief introduction to Alzheimer's disease, and then I'll focus on two works. One, which is basically testing out some architectures for using MRI data. And the second one is using spectrograms, okay, of EEGs. And that's it. So first, that's the name of the project, Machine Learning for Mental Health, New Developments and Applications Using Multimodal Data. This, in fact, this project is now finishing. It started in the late 2021, and it finishes next month, I believe. And it's based in my university, UAI, and it's led by Professor Rolando de la Cruz, and I'm in charge of one of the research lines associated to using deep learning for this project. Okay, and it basically has researchers from neuroscience side and also statisticians and machine learning guys like myself. Okay. And in particular, the two works I'll be presenting is part of one of my PhD students' work, which is Mario Bravo Ortiz. He's at University Autónoma de Manizales in Colombia. And I co-supervise the student with Reynel Tavares, who's my former postdoc, and he's an assistant professor there as well. Okay. Good. So Alzheimer's disease is basically a progressive neurodegenerative disorder that primarily affects memory, thinking, and behavior. It's the most common cause of dementia. You can see they're accounting for roughly 60 to 80% of the cases. And AD leads to brain atrophy and loss of neurons, especially in the regions of the hippocampus and cortex. Here, you can see this is an image from Wikipedia, this illustration, but on the left it's the normal brain, on the right you have the Alzheimer brain. Noticeably, you can see there's a shrinkage in the hippocampus, ventricles are significantly enlarged, and also the cerebral cortex is also shrinked. Okay, so that's very characteristic of an Alzheimer brain. Of course, symptoms worsen over time, progressing from mild memory loss to severe cognitive and functional decline. And Of course, although this disease is incurable, it's still in demand and very in need to conduct early diagnosis and treatment can actually slow progression and improve quality of life. So the earlier you're able to detect, the better, okay? So the conventional approach to do AD diagnosis is a multi-step clinical evaluation which combines cognitive tests, clinical judgment by the medical professionals, and also supporting biomarkers like MRI and also cerebral spinal fluid analysis, okay? And of course, this approach sometimes can be subjective, expensive depending on the testing you're using, and also even invasive, okay? So even after all of this, it might not even be able to detect the disease until it significantly presents brain damage, and therefore we're too late, okay? So given all these, more, I don't know, negative characteristics or complications to this problem, it's of interest in this case to use a machine learning approach, in particular deep learning, for early and more accurate detection. Okay? So that's part of the motivation of this approach. And so the first work is basically oriented to, can AI help us see what the human eye can't? Okay? So the first work I'll be talking about is related to Alzheimer's disease classification for the different stages using MRI and trying out existing architectures and also custom made by our group, okay? Now, MRI, of course, is capable of showing brain atrophy, and also it's non-invasive, like the CSF I mentioned before. And deep learning, well, we saw that traditional diagnosis is subjective and limited, whereas deep learning models can learn subtle patterns and not visible to clinicians, okay? And so this is a work from 2023. This was one of our first works from our group. And so the goal here of the study was to classify stages of Alzheimer's disease. On the bottom row, you can see MRI images of clinically the control group, okay, or cognitively normal. And then as we move upwards, it starts increasing. The EMCI is early, mild cognitive impairment. Then we have mild cognitive impairment, late mild cognitive impairment, and at the top row, we have Alzheimer's disease, okay? So these are 3D brain MRIs, and the idea is to try different architectures for this. And of course, ideally, one wishes to be able to classify correctly, you know, images coming from this category here, which is the early mild cognitive impairment, okay? Of course, working with MRI requires quite a lot of pre-processing. Now, because we work directly with MRI, the several of our deep learning layers are able to manage some of these pre-processing. The data we use for this paper essentially are the two main current sources of data to conduct research in Alzheimer's disease. One is the ADNI, and the other one's the OASIS data sets. So for this work in particular, we used 2,559 MRIs scanned and from 1,126 subjects, okay? Pre-processing, there's an interesting software called FreeSurfer, which basically does all the basic pre-processing of the MRI, like skull stripping, anatomical registration, and several of the other data augmentations, okay, like we see below. On the right, you can see the distribution per class. So there's a bit of imbalance, but we tackled this, we'll see later on, with our loss function using a weighted version of the cross-entropy loss function, okay? The data partitioning, this is interesting also because in order to reduce data-induced biases in the model, the idea is when you do the data partitioning into training, validation to search for the hyperparameters, and then the testing, it's done at the subject basis. This means that each patient goes, there are several registrations of the MRI at different stages, and all the images belonging to one patient is only appears in one of these sets. It's either all their images in the test set or all their images in the train set, but there are no mixing images from the same subject. Okay, and you can see there the distribution. Also, we see the range of the ages are roughly from 55 to 95. About 54% of the data from male and the remaining 46 from female. And also we can see we also did the partitioning so that the age distribution is more or less the same per each partition, okay? So the deep learning models, essentially in this paper we tested 4 architectures. The first one is homemade. This was produced by us. This 3D CNN, which we see Siamese on the right. It uses 3D convolution. So typically many of the convolutional neural networks used for MRI, people take out slices of the MRI and then work with the conventional 2D convolution. So in this network here we use the complete MRI file, therefore we're applying 3D convolution. You can see there the typical combination of conv 3D with batch normalization and average pooling for reducing dimensionality. And so that was our architecture we devised, and then we compared this to other popular models, to an efficient net B7, the dense net, and also another class of deep learning models like vision transformers, okay? Which, like it says there, has this attention-based model, which is able to give more, it's not very good for local features, but it's very good for global context of the entire image, okay? Now, to develop these pipelines for medical imaging specifically, there's this MONAI framework, which is Medical Open Network for Artificial Intelligence. So all the pipelines that you develop for training and also like data augmentation, flipping and so forth, you can do it within this framework. And we use the ADA Delta optimizer, which is a class of stochastic gradient descent, but it actually has the learning rate per dimension, okay? And like I said before, we use the weighted cross entropy loss in order to manage the class imbalance, which wasn't that severe, okay? Good, so some results from this. So first, when we compared the control group with Alzheimer's disease, which is basically the class where it's too late, okay? So here the differences, morphological differences are quite clear. And so therefore, we can see an accuracy, a high level of accuracy. And in this case here, the best model in this case here was the vision transformer, okay? So the vision transformer obtained almost 90% of correct classification for this binary classification problem, okay? So, but again, this isn't so challenging. Whereas the more challenging one, which we want to classify between control and the early mild cognitive impairment, we can see a significant drop in the test accuracy. And here the best model was the model we proposed, the Siamese 3D network, okay? Obtaining 67%. So straight away you can see there's quite a big gap for improvement in this sense, okay? Then when we tried the multi-class classification, taking into consideration control, the mild cognitive impairment, and then Alzheimer's disease, then the accuracies for all the models are even lower. Of course, now it's a 3-class problem, so here the range of the accuracy is between 55 and 59, and we see the efficient B7 net is the one that obtained the highest result, but isn't that great. Okay. So from that work there, essentially, well, we started exploring different architectures. We only use MRI as input. So the idea there is because it's accessible and it's less, I mean, it's expensive, but it's less expensive than other types of scan like PET. And of course, the limitation of, we see the performance is still a moderate performance on early stage classification. And of course, one always wants to have a lot of data to increase the generalization power, but again here, our sample size is still small, okay? And then from that work, the future directions were to use larger data sets. Like I said before, annotated larger data sets is not that easy to obtain. But the other two methods, test interpretability methods and also explore hybrid models, which combine convolutional networks with vision transformers, was something interesting at that time to 2023. So we started working on these 2 points. And we generated a new model, the following model, which I'll present. So the second approach here is to actually see if we can diagnose Alzheimer's using electroencephalography, EEG, as if it were like an image. Okay. So in this case here, that's the name of the work, SpectroCVT-net. That's the network we propose. Here the idea is to work with EEG. So this is a more cheaper approach. It's a non-invasive technique that records the brain electrical activity using electrodes placed on the scalp, like the image we can see there. Here it affects 128 electrodes. And so this will give way for each channel. We'll have the signal here. Here we're only seeing the first 20. And of course, EEG compared to MRI is even more, it has lower cost. It's portable to be able to conduct an EEG exam, and also safe. And of course, it's especially interesting for low resource settings. But unfortunately, of course, EEG signals are noisy, complex, and in many cases hard to interpret. Okay, so this was like the challenging part from this work. Okay. Here, the objective was to, of course, propose a new architecture for this problem. Here, because we're going to use another data set, which I will explain in a bit, this data set doesn't have like different stages of Alzheimer's, but in fact it has different types of dementia, okay? So in this case here, we are going to classify between Alzheimer's disease, behavioral variant, FTD, frontal dementia, and healthy controls using EEG-derived spectrograms. And of course, like I mentioned before, combine characteristics from both worlds of these models, local features with global dependencies, which we obtain by vision transformers. So here, the data set we're using is a data set called BrainLet. It's generated by a consortium, a South American consortium named RedLet. It has, at least the data set we're using now, 780 patients coming from samples from these countries here. And in fact, it has EEG and MRI and also has cognitive testing. So it's a multimodal data set, okay? And it has the healthy control, Alzheimer's, the behavioral variant, frontotemporal dementia, Parkinson's disease, and multiple sclerosis also as a disease. And so we have, in particular for this work, we had 86 EEG scans. And here you can see the distribution of, for each class of the number of patients, okay? Yeah. So the pre-processing here is it's interesting because instead of working directly with the EEG signal, we see that most of the work nowadays is trying to convert all types of data into images, okay? And so for this, in this case here, for the signal transformation, we use this short time Fourier transform. Here the EEG is a non-stationary time series, meaning that the frequency content can vary through time. And so therefore, if you want to capture time and frequency characteristics, you perform this STFT transform. And so this will generate like this is one signal, one channel. We will generate this image essentially, which you have on one axis the time and the other the frequency. And then because we have 128 channels, you can stack these to form this 3D multi-channel cube of data, which is basically what we generated for training our models. So these are 24 by 24 images with the depth of 128, which are the actual EEG channels. Okay. There is no truncation, and so we preserve full signal, and also we use some interpolation to resize and uneven widths. Okay, so because we need to build this cube with the exact dimensions. So the spectral CVT net architecture, like a high-level diagram is on the top. It consists first of blocks for feature extraction. Each one of these green boxes we see here is this here, okay, which is basically a stacked convolutional 2D with batch normalization, Ricci-Rielu, which was talked a bit before, and then again the same. We have these skip connections here, and also what's very, very interesting here is this little red box here, which is called a squeeze and excite block. And this allows for channel attention during the learning, meaning out of the 128 channels, this block here is actually responsible of pointing out learning which are the more meaningful channels useful for the prediction, and try to weigh down the ones that are not actually useful for the challenge. Okay, so this here, which is the smallest, is the most important in the feature extraction. And so we repeat this 4 times. Then you end up with the convolutional vision transformer, which is here, which essentially is composed of the CVT, which combines the convolutional projections with attention heads here of a classical vision transformer. Here, essentially, vision transformer needs to flatten it needs to use small little squares, patches of the image, which then you need to flatten. And although it has this positional encoding, it will know from which part of the image each one of these small squares come. But within the image, these little squares, you lose the spatial relation. So that's why the convolutional part actually makes sure to have interesting features which then are flattened used by the vision transformer. Okay? And then all of this is basically to generate better representation of the data, which ends up being a feature vector, which goes into a dense net, which is basically is for the classification. All of this end to end is trained all together, okay? And so and then in the end we have a softmax layer for the 3-class problem. So the results in this case here is interesting. First, if we this architecture we proposed, the spectral CVT actually beats all the other large models which we consider even with the transfer learning approach. These are all 6 other quite big networks which has been pre-trained on ImageNet and then only trained with the images for the classification part. And first, so we can see Alzheimer's disease against the healthy control. We have actually quite a high accuracy, even though this, we said, it's not that challenging, but is significantly better than what we obtain with MRI. Then the BVFTD versus health control, healthy patients, it's 100% accuracy here. We were able to, this was done with 5-fold cross-validation, sorry. And then AD versus this other type of dementia, 85%, okay? And the multi-class problem, 92% of accuracy. Now, what's interesting though is that the number of parameters is significantly smaller than the other competing models. You have the one on the end of the right. This has almost 200 million parameters. Ours is only roughly around 12 million. And then for the interpretability, sorry, we use GradCam, which is this approach that is able to weigh each channel regarding the output of the classification. So, so we're able to identify relevant EEG channels and frequencies per class, okay? So here, eventually, what we see with GradCam analysis, we're able to identify, well, what levels of frequency the AD focuses on. And basically, we can see here on the gamma and delta ranges of the wave. And also, this allows us to identify most influential electrodes per class. So, for example, in the GradCam here, this one here represents what part of the frequency of the spectrogram of the image is the model using to identify that this is Alzheimer. And this here actually is associated to this electrode here, okay? So this actually helps to transparency of AI for decision making, and also assist neurologists for, you know, especially in resource limited settings where you don't have too many tools for the analysis or to be able to use MRI. Okay? So a conclusion for this part here is basically we see this spectro CVT net achieves state-of-the-art results in EEG-based Alzheimer's disease diagnosis. It combines CNM with vision transformer and channel attention for robust feature learning. This is one of the first application of this brainlet database using deep learning models with the EEG data. And so now currently we just submitted yesterday or the day before, we're doing now multimodal approaches where we're combining our network using the spectrogram approach, but now combining with clinical data and of course the MRI images, and that's another work, okay? Probably, of course, lots of GPU resources. I didn't go into detail with that. For this work here, basically, we used A100, NVIDIA A100 for most of the training, and with 45 gigabytes of memory, and also for the smaller models, the NVIDIA T4 GPU. Okay. And I think that's about it. So thank you for your attention.
Okay, thanks, Gonzalo, for the nice talk. We have time, Claudio, and yeah.
So thank you for the talk. I have just two quick questions. First one, in the first and your first research, your first result, right? Mm-hmm. You say, well, we have this amount of accuracy. So what is exactly the target that you are using? I mean, the output. I mean,
right. So yes,
the last line. I mean, the last line of images.
Yeah. No. So here, so you mean the label of the? So each image has been previously classified by using the standard approach. So it's been validated by several groups. The ADNI base is from US and Canada. It's like 60 clinical institutions that have given data, and so it's validated labels. And so the output is basically in a binary classification, you know, the probability of being one class or the other.
Okay, so you
So
show it.
binary classification uses a sigmoid activation function and
Yeah,
the
yeah, but
multiclass.
you
Yeah.
show it different stages, right?
Yes, yes,
So those are the targets you want
yes,
to. Okay,
yes.
perfect.
Different stages. Yeah.
Okay, perfect. And in the second one, can you explain a little bit how do you arrive to that architecture, or it's
Yeah.
something?
So it's a bit. So yeah. So here there's some math behind it, and not so much again. It's a lot of trial and error. It's also based on some other works that have started to exploring. For example, the first case, the Siamese approach, has been used in for other medical imaging, and the actual architecture then will depend, of course, of the dimension of your image, and how many convolutions and aggregating pooling stages you can use in order to reduce the spatial size of their image. And then when it's too small, then you flatten. So the level of that will depend, of course, of the resolution of the imaging. I didn't say that for the first work, the MRI were resized, reshaped to 91 times 91 times 91. Okay, and for the second one, again, it's basically trying to see how the more blocks you start adding, the better feature maps you obtain. But there's a spatial limitation, so basically that's when you stop. And of course, you don't want to overfit. So that's another of the big problems. Yeah, but it's that's the validation sets for trial and error. Yeah.
Sí, hay que prenderlo. Abajo. ¿Hacia arriba?
Ahí está. Gracias. Era mi error. Ya, tenemos tiempo para una preguntita más.
Thanks. I would like to do two questions.
Yeah,
But
yeah.
quick questions.
Yeah.
First of all, thanks, Gonzalo, for the presentation. In which ways could neuroscientists and expert knowledge aid the construction of your model?
Yeah, so that's a very good question. I think, especially for the output, from the interpretability point of view, basically for us to know what type of visualization they're interesting. I mean, they won't go too much. I mean, you have people from neuroscience who are actually working on the actual neural network type model inspired by biology. But in this case here, it's mostly their contribution is for what type of visualization of the output is useful for the interpretation. So GradCam visualization is like standard, but in the work we just submitted previously, we're also combining clinical data. So we're able to do like a CHAP value analysis of the clinical features combined with the imaging. And so that's something that the actual people from neuroscience were interested in being able to see.
Good, great. And also, have you considered the use of neuromorphic computing?
I mean, it's oh yes, of course, it's an option. I mean, I would need another student for that, of course, but yes, I mean, for this year there are several approaches that they've been trying out. So yeah,
good.
But it's not something I've been working on. Yeah.
Okay, thanks.
Okay, so let's thank Gonzalo again.
Thank you.
And we move to the next talk. Okay, maybe I can start presenting our next speaker. So our next speaker is Joaquin Fontbona from around here, from CMM. Joaquin is sort of at the moment, he's sort of right in the middle of this session, I guess, because he's a probabilist, but he has been moving to trying to work towards trying to understand some mathematical foundations of machine learning. Yeah, he's also the director of the CMM data lab, and he has lots of experience also in applied projects in data science, as well as a long history in in probability, in mean field models, and optimal transform, and all of that. So, Joaquin.
Okay. Thank you very much, Daniel, and thank you very much for the opportunity to give this talk in this celebration of CMM's birthday. Yeah, so as Daniel was saying, I will present something which is in the middle, so to say, between probability theory and neural networks. This is part of, it's based in a joint work with Javier Mas, who was a former student of mine, master student. So let me first give an idea of what's the idea, what we were interested in. So yeah, we will be interested in understanding what is the role or the influence of symmetries of the data in the learning dynamics of large neural networks. Okay, when I say large, I mean in a specific sense, which means the width of the networks going to infinity, and I will explain why that limit is interesting. Okay, so that is what we will call the mean field limit of artificial neural networks. Yeah, so this is an overview, but I will just start by explaining these ideas, why we're interested in this limit. There are some theoretical objects which appear also coming from probability and PDE called the Wasserstein gradient flows here, and how they appear in the concept of supervised learning using artificial neural networks. Then I will explain a little bit of the interest of symmetries, both in the data and in what is called the symmetry leveraging techniques, which are techniques used to train neural networks or to design even architectures of neural networks in order to take advantage of potential symmetries which are in the data. Okay. And I will overview some of the results we obtain in this work, in particular how this symmetry impacts, or these symmetry leveraging techniques in training impact the dynamics of the training and the structure of the optimization problem that you are solving at the end. And then we will obtain some, I would say, takeaways, still theoretical, but some consequences that are interesting on their own that could be useful for some practical applications. Okay. Okay. So the context is the following. As I said, we're talking about supervised learning with neural networks. So let us imagine we will always talk about a feature space, which is what I read, what I give to the neural network. There are the labels. So each vector of features, in this case, it's an image, has associated a label. In this case, it's this is a dog, and I want my neural network to learn, given a photograph, the position of its nose. Okay, and there is this parameter space, which is what happens internally in each unit, I would say, of the network. Okay, so we model this probabilistically. We have a distribution of let's say pictures of dogs with its nose, and we will use a convex loss function that will be used to measure how good our predictions are once we have trained, and it will be used to train also the neural network. Okay, so yeah, and we will always be using what is called a activation function, this is a very general way of describing it. It's really, I mean, activation functions, you already heard of them. It's really what each neuron does with the information it's handed by the previous one, let's say. But here I really call activation function what the whole system does. I give it an input. I have some parameter in my unit, in my neural network, and each of the units of the neural network, and then it gives me some label, some predicted label, okay, some answer. So what I will be focusing in is, well, specific, I would say, quite simple family of neural networks, in which we call it shallow models, but I will be a bit more specific of what it is. But mathematically, we write it like this. We have, there is a set of n internal units, let's say. Each of them has a parameter. And, well, what is the output of my network? I build a function, for each of these vector of parameters. This gives me a function, and the output is the average of this of the different computations done by each of the units. Okay, this could be in a Hilbert space, or I mean, it doesn't need to be real value. And you can see that this is actually an integral with respect to the empirical measure of the parameters. Okay, we will write it like this. So these are the models or the functions that we are using to predict this. I mean, I want to give this input, and I want the network to give me this point. Okay, we are considering functions of this type in order to learn them to do this. Okay, so this is a something also, maybe I will show it here. A particular case is what is usually called a shallow neural network, okay, where you really have one hidden layer, okay. So you have this is a linear layer, it's called linear layer. You have this activation function which acts coordinate-wise. These are the classical ones. And what I'm doing is a generalization of that, because actually I will have an ensemble of internal units, but each unit can be something very big. It could be a convolutional neural network itself, a multi-layer perceptron, and so on. Okay, so that's my setting. And okay, so each of these could be a multi-layer neural network on itself. Okay, my output is the average of each of their results. And an important object here, from the theoretical point of view, are what are called Baron spaces, which is doing the following extension. I will not only consider empirical measures, but I would consider integrals with respect to any probability measure on the space of parameters of the network. Okay, and this is important because this allows us to go to the infinite or the very large number of neurons. Okay, I put everything in a space that contains neural networks of any number of units, internal units, and also their potential limits, let's say theoretical limits when the width goes to infinity. And there is a well-known property called the universal approximation property, which in some cases does hold, which tells you that for suitable activation functions, this space is dense in certain functional spaces, which tells you that it is possible in principle to approximate any function of labels, of features giving you labels, in terms of these objects, okay? And since you can approximate these measures by empirical samples because of lower Chern numbers, this tells you that you can also eventually, in theory, approximate any function with a finite but arbitrarily large networks, okay? Okay, so what is the supervised learning problem? You want to, what you want at the end is to minimize this population risk. So what is the population risk? Is for, if I take some new data point, not seen before, well, I would like this to be small. What is this? Is the loss, the error I make when given this data. I suppose that this is should be the output, but it actually, the label is y, okay? What happens in practice is I don't have access to pi, to the distribution of the data, but I do have access to a sample, okay? Could be images taken from some data base or whatever. And I would say the most conceptually fascinating aspect of all of this is this function, this population risk as a function of the vectors parameters is highly non-convex. It's really, I mean, very far away of being convex. It's a very high-dimensional function. Well, so it's hard to optimize in the case. You cannot expect to let's say, do some gradient descent algorithm and reach the global minimum. Nevertheless, that's what people actually do. Not exactly a gradient descent algorithm, but stochastic variants, like a stochastic gradient descent, or some noisy variants. And the idea is that since you have access to points, you use, instead of using the gradient of this that you cannot compute in terms of theta because you don't have pi, you used one single point in order to do one further step of the algorithm, okay? So in the case of neural networks, this is what is called the time step in general, and in the case of neural networks, it will be of the order of 1/n, Okay, and this is the noise. What is called if you want to do some what is called Langevin stochastic gradient dynamics, which can take you out from local minima easily, for instance. This is a penalization, but this is more or less trying to minimize the function, and we would have theoretical guarantees if the function was more or less convex. Okay. Yes. What else? Okay. So this is what is done all the time with neural networks. So I will start from this key idea, which has been already developed for several years now, is that okay, this problem is not convex. This as a function of theta is not convex, but you can leave this problem not to see this as a function of the parameter theta, but as a function of the underlying distribution of neural parameters of the network. Okay, so if you see things like this turns to be a convex function because this was an integral with respect to mu, and this is a convex loss, and then you take an expectation. Okay. So you are lifting the problem to something which is infinite dimensional, but it becomes convex. And instead of looking at the dynamics of the parameters, the vector of parameters in your stochastic gradient descent, you look at the dynamics of the empirical measure of parameters. Okay, so you forget about the labelings of the coordinates. Let's say you just look at the population of parameters. And it turns out that this is my starting point. I hope I haven't exhausted the time. 14 minutes. Okay. I left. Well, it's the same. Okay. Okay. So but I wanted to explain this with some detention. So this is the starting point of what I'm going to say, or what I would like to explain. Okay. And this is a little bit why the reason why I came to this topic too, because I used to work in what are called mean field models. And this gives you a theoretical framework to understand what happens when you when you look at this population of, I would say, particles. Okay, representing here the neurons parameters, and you try to see what happens when you make their number go to infinity under some conditions. Okay, and actually here the interesting point, the key point here is if you can see that each of the parameters. So from 0 to n, in its dynamics, it interacts with all the others, because here we have all the other parameters, but the interaction is of the size of 1 over n. Okay, so that's what's called a mean field interaction. And what you expect is that the empirical measure of these objects stabilizes in some sense with when n goes to infinity, more or less in the same way as in the law of large numbers, except that here you don't have independence from the beginning. Okay, there is kind of an asymptotic independence that you obtain. So the result is that suitably normalizing here, this should be n, epsilon n is n, actually it's because of the 1 over n. If you look at these dynamics in the right time scale, you will see that this converges to some continuous flow of probability measures in the space, in the Wasserstein space of probability measures. And this flow is minimizing a function which is called entropy regularized population risk, which has this dynamics has a very explicit form, which is here. So the Wasserstein gradient flow actually solves a partial differential equation, which is Makin-Blasov type. And things are very, very explicit, and you can say a lot of things about these dynamics. I would say the most interesting one is that this function. This was the population loss. This is due to the penalization. This is due to the noise, the fact that you have an entropy here, and this turns out to be a convex function. Okay, so if you leave the problem to the space of probability measure, stochastic gradient descent is running a gradient descent in infinite dimension of a convex function. So you can expect there to be some convergence to a minimum, and actually, in some cases under some regularity assumptions, you have it. Okay, so this is telling you why, at least for shallow models, this optimization should be doing what you want. you are minimizing the population risk modulo some regularization. Okay. Okay. What about symmetries? Yeah, I will try to give the main ideas here. So typically your data has some symmetries here. You would like this to be, I mean, you know this is a dog, you know this is a dog, and you would like, for instance, here the position of the nose to be, I mean, if you rotate the dog, the nose rotates accordingly, let's say, okay? You will also think that you have translation, and typically in pictures you want to identify some object, and it could be anywhere in the okay? And we also will speak, I assume that I have an action of a group here, it's rotation, that could be anything, compact. So in the features and labels. And I would say that the data is equivariant if, well, it's after applying any of the group elements, the lowest is the same, okay? So people try to take into account or take advantage of the symmetry of the data or the supposed symmetry of the data with several techniques, let's say, during training. One of them is data augmentation, which was already mentioned, in which you give the neural network not just the original samples, xk, yk, but you also give them in all the possible rotations. There is something called feature averaging, with actually what you do is to train several models at the same time, okay, with different versions of them, and then you do some average pooling, okay? And then that is the version that you expect to be better as a predictor. Of course, yeah, the idea is to give some, let's say, inductive bias to the network, in the sense that if you know that there is symmetry, you would like to help it to find that symmetry more easily. I would say the more important technique is what is called equivariant distribution, which is actually what's behind convolutional neural networks, graph neural networks, and other architectures, where actually, well, what's the idea? You realize that there is also an action of the group on the set of parameters, and well, the good actions should be compatible with the activation in this way, which we call jointly equivariant. But the point is the following: what equivariant architectures are? They correspond to functions of the parameters of the neurons. Consisting in, I mean, the parameters are of this type. There are fixed points for the action of the group, okay? So what you actually get, I will skip some details here, but this could give you a huge reduction in the dimension of the parameters, okay? Because you will, this translates into a parameter sharing scheme. You have lots of parameters which are repeated, okay? And what you would like to, what you aim at is that the neural network automatically identifies the same object in different, let's say, translation or rotations. Okay, it's from the beginning it's like that. And yeah, I just wanted to say that this is all of these training techniques amount to some modification of the population risk. Okay, so with the this is an averaging well. At the end, this is an averaging. This is an averaging of the function. This is an averaging of the risk. And here, what you're doing actually, when you do this, is that you are projecting you're doing a projection on this subspace of fixed points. Okay, and that is what you are minimizing then. Okay. How much is it? Like 5 minutes? Yeah, 10. Okay. Okay, so this led us to consider what are the notions of symmetries that are acting on the parameters when you consider these functions, these functionals and these equivariant architectures. And it turns out that, well, you can do this theoretically all the time. You have your space of probability measures on the parameters, and okay, there are two operations that are important to us. One is the symmetrization, which is really pushing forward the parameters for the action of the group and then integrating, averaging, and there is a projected version which is really projecting to the space of fixed points. Okay, so this gives us two subspaces, and we call them weakly invariant, which is when your distribution is equal to the symmetrized version, and the strongly invariant is something much more rigid, which is when they are concentrated on the space of fixed points, okay, for the action of the group. So first remark is that when you symmetrize a given probability measure on the parameters, you're actually obtaining the closest equivalent function to the original one. Okay, if this is the function that you have constructed in terms of mu. Well, if you symmetrize the measure, you get the closest equivalent function. Okay. This is an example of what the two notions are, which is really quite simple, but clear enough. Here the action is flipping the sign, so the weakly equivariant measure corresponds really to having this they're asymmetric. Okay, so really you have this here. If you have the delta mass, you have the average of the two versions, let's say, of this parameter. And in the case, what are the strongly invariant is really taking the parameter 0. Okay, it's projecting to the fixed point. Here, the fixed point of this action is 0. Okay. Yeah. So first set of results. I will go very quick, but actually you can really tell what's going on, what's going to happen with these functionals. What could be the relation between them? We will assume that this equivariant property of the activation function, and you can show that you have the coincidence between data averaging and the fact that you are symmetrizing the risk like this. You have a coincidence between feature sorry, this was data augmentation. This is feature averaging, and here you are symmetrizing the measure. And in the case that your data is already symmetric, which I write like this, your function turns to be invariant, and everything coincides. All of these different variants of the risk. Okay, and then applying data augmentation or applying feature averaging in the training stage is the same as optimizing over the parameters which are symmetric. The measures on parameters which are symmetric. Okay. Moreover, if you use data augmentation and feature averaging, well, I mean, you could use it even if the data is not equivariant. Okay. So if you do that, you are forcing the optimum to be found or to be searched in equivariant models, and actually you are obtaining the projection, the closest possible symmetric model. Yeah, and so actually, if your data is symmetric, it doesn't make any difference to do data augmentation, feature averaging, or nothing else. Okay, in the mean field limit, in the large infinite wide limit. And what happens with the strongly invariant measures? Well, I mean, they are interesting because they reduce the dimension a lot, but they could not be good because they are not flexible enough, or they don't approximate the data. So you need what is called a universality result for this subset of function, and then you can say that it's also a good architecture. But in general, yeah, you have this. Okay, so minimizing using equivariant architecture should be strictly worth. Okay, even if it's faster, but it won't be necessarily a good predictor. And then we studied what happened with the dynamics. I will be faster here, but roughly the dynamics also coincide. I mean, the values coincide, and if you start in this case, we start from invariant distributions in the weak sense. The dynamics and the global minimum will be the same. Okay, and again, yeah, for the two techniques, data augmentation or feature averaging, and if the data is symmetric, it's already the same. The more interesting, I would say, point is what happens with the strongly invariant measures. Then you would like to stay in the space. So instead of considering noisy stochastic gradient dynamics with arbitrary noise here, you need to project the noise because otherwise you will leave the space. Okay, so this gives you a restricted dynamics in this smaller space, and you have a similar result in the sense that if you stay there, if the data is symmetric, or if you do any symmetry leveraging technique, the dynamics will stay in this smaller space. Okay, which is interesting is if the data is already symmetric, you don't need to do anything; it will stay there. Okay, so this is a really, I would say, a phenomenon for the infinite n or close to n large enough, because this part can always leave the space of parameters. Okay, for finite n, but for large n, it will stay. Okay, and let me just comment on some results here. So these are numerical results, but roughly illustrating what we were seeing. First of all, well, all of the results that we are seeing. This is just to say that it's a large n phenomenon. You see the distances, this fact that the dynamics remains on these subspaces. You really see that when the number of neurons starts to be large. Here, these are like small, what are called teacher-student models that we are really like doing some. It's a toy model, but we have, I don't know, dimension of the parameter of each of the neurons is 4 in this case. The action is very simple. It's flipping. So here is a graph of what you can see. If so, these squares are what are the positions of the ground truth, let's say, which is the teacher model. I construct a simple neural network with these fixed parameters. Okay. And then I train my neural networks and I see what they do. So if I don't do anything, this is the space, by the way, of equivariant, the fixed points. Okay, so this is a 4D plot with the colors, and this is the subspace which is the fixed point. Okay, so if your data is arbitrary and you start in this space, well, the particles will leave this space. Okay. On the other hand, if you do some symmetry leveraging technique like data augmentation, interestingly, as the theorem says, it will stay here in this space of fixed points. Okay. More interesting, I would say, is the other result, which tells us. Yeah, we have this other result that tell us that. We can use this result in the following way. What we call an heuristic to find parameter sharing schemes. What does it mean? If we have, assume that we have symmetric data. So these points, the squares, are data which correspond to a symmetric model. Okay. So I will start in a space of fixed point, which in this case is just 0. Yeah, the origin. This acts by orthogonally, so everything is understood in terms of subspaces. And so if I start with my points here, so in this case the data is symmetric, and I run my training, we will see that at the end of the training or after some time, my particles went all to this other point. Okay, so this is telling me that I can use a larger space. A larger space means more expressivity and so on. So I would like to find a better space than this one. Okay, but I didn't leave the space of fixed points. So what I can do is now to take the space generated by my original point and the coordinates to which my particles escape. So this gives me this subspace, which is here, and then I run again my training, and I will see that the particles tend to occupy as much as possible the space of fixed points. Okay, because the data is telling them that there is less symmetry than we thought at the beginning. But all the time, we still will be in the space of fixed points. So the idea here is we get this an heuristic in order to find, I would say, the biggest possible space, as suggested by the data, which has the right symmetry. Okay, and that means the most expressive equivariant architecture. Okay, so those are the summary of what we did. Interesting questions that are open is to quantify the convergence to these limits in the mean field, n going to infinity and t going to infinity, and compare them in the three cases, because that will tell you what is algorithmically more efficient or more accurate. Yeah, and there are some theoretical questions in terms of guarantees, and we would like to apply this in a setting of more real data and large data sets. Okay, that's it. Thank you.
Any questions?
Very short question. In the step size with the perturbation with the Langevin process, then you have variance uniform or local uniform.
There is a function actually. You can make it. There is a function multiplying in the time derivative of and the limit. You can tune to have general functions. But the thing is that if you really want to converge to the optimum of the functional, or you need you cannot turn off the noise as you would do in.
Yeah, but the noise has uniform bounded or not.
In what sense?
The noise, the variance is uniform bounded.
Yeah, it's more or less uniform. Yeah. Actually, to converge to the Gibbs measure, you need it's more or less uniform. Yeah. Should be.
Any other questions? A very short one. But is it reasonable to expect that in terms of performance, the neural network, the architectures which encode the symmetries, I don't know, I don't remember the name. Should those be better or?
Yeah, one obvious reason, let's say, of natural reason why it should be better, the one with the strong symmetries is that the dimension is much slower. Okay, so in any case, you would expect, I didn't say, but the kind of result that we need in order to obtain convergent bounds, they more or less exist I mean, it depends on functional inequalities like log-SO, and stuff like that. So there exists in other contexts, I would say, and you can track the dependence on the dimension. Okay, so yes, there should be a trade-off, because if you reduce the dimension too much, you won't have enough. I mean, you won't generalize well. Okay, so the actual point is to find the trade-off between all these parameters. Of course, that works very well in all the equivariant architectures that are widely used. Like, I mean, we know it works in some cases, and people have found how to do that. But would like to understand a bit more how that should be done.
Okay, so let's thank Joaquin again.
Thank you, Matt.
Okay, so for the last talk of this session and of the morning, we have Jerónimo Uribe, who's also visiting us from an international research lab of CNRS. So he's a professor at UNAM and the director of the La Sol lab. Jerónimo is an expert in Levy processes and branching processes, and he's going to talk to us about a pathways approach to time change.
Thank you very much. I am really thrilled to be here at the 25th anniversary of the first IRL.
You have to move it up a little bit.
Okay. Is that better? Good. So really thrilled to be here at this 25th anniversary of the first IRL. It's been really eye-opening to see what an IRL can be given enough time. So thanks a lot for the invitation. Good. So where's the... Okay. Good. So I'm going to talk about stochastic analysis and stochastic processes. I'm afraid this is going to be a very theoretical talk. Also, this slide is just here to show you that I can use Beamer, but I actually prefer not to lately. So it's going to be a handwritten talk. Good. So what is this time change? I'm going to motivate it by something that's been recently called regularization by noise. So take an ODE, ordinary differential equation, like the ones that's written here in probability notation. So x prime is b of x. right? And of course, there's a very classical theory for existence, uniqueness, approximation of these things, but they usually require this function B to be regular, like Lipschitz continuous or something like that. So what happens when you have non-Lipschitz functions is that automatically you can, for example, break uniqueness or even break existence when this B is only measurable. So in this precise example of a function, 0 is a solution that passes through 0, but so are all of these solutions, and all of them do not remain in 0. And using these two types of solutions, you can actually construct one-parameter families of solutions to this very simple ordinary differential equation, right? So you can check that out in the lecture notes by Flandoli in this very French and interesting probability summer schools that have been going on for quite several decades now. And yet, in 2007, Davy obtained this very interesting result. So instead of this time homogeneous drift, consider a time inhomogeneous drift, f, which depends on t and x, right? And all you need to assume is that this drift is bounded and measurable. So then for any starting point, you consider the random ordinary differential equation, which starts at x, and then, well, x prime is f of t comma xt, except that you add some additive noise. And you add this additive noise in terms of the increments of a Brownian motion, right? Then you consider the bad set of realizations of your Brownian motion, such that the random ordinary differential equation does not have exactly one solution. So you might have 0 in the case where there's non-existence, or you might have multiple solutions. Right? It turns out that this n has probability 0. Right? So you just add this very trivial additive noise, and then you automatically get existence and uniqueness. So I'm interested in this type of phenomena. And of course, what's the dream of Flandoli for being interested in this type of result? So one thing he actually sets this as a goal in this lecture notes is to consider the equations of fluid dynamics, right? Add some type of noise, and then produce a well-posed problem, existence and uniqueness, right? We're going to be a little bit more humble in our goal. And our objective in this talk will be to generalize Davis results to show that multiplicative noise can also regularize. So I'm going to say what multiplicative noise means in a bit. So that's motivation 1. I'm going to switch to motivation 2, which is a population dynamics model. So we're going to take, say, one initial individual, and individuals in my population will live for an exponential amount of time. So that's lifetimes are exponential random variables, all of the same parameter, which I'll call lambda. And at the end of their lives, these individuals, well, they die, but they leave a certain random amount of offsprings. So the probability of leaving j offsprings is going to be mu of j. Right, so here you have this individual, it dies, gives 3 offsprings here. This middle one is the first one to reproduce, well, to die and reproduce. It gives rise to 2 individuals. And what I'm really interested in is in the size of these populations at all instants of time. So in basic courses in stochastic processes, we can note then that the process giving us the population time sizes is a continuous time Markov chain, right? That it has the same jump sizes as the simplest continuous time Markov chain, and that would be a random walk, but that the jump intensity, the total jump intensity, is actually proportional to the state at which the process is visiting at a certain time. So jump intensities are proportional to the state. And yet the idea is now that we can relate this kind of simple building block to construct a more complicated model, the more complicated population dynamic model. So it turns out that you can actually do this. What you need to do is to accelerate this random walk, right? So when your process is at state k here, you notice that this integral would just be k times t, right? So you're basically accelerating the jump times of this process x, and that turns your exponential random variables into the ones having the correct parameter, so that the solution to this random ordinary differential equation is the stochastic model you were interested in the beginning, if your x is just a simple continuous time random walk. So these are the types of equations that I'm interested in. Good. So this has a generalization known already from the 1960s. This was work of Volkonsky, who actually considers, well, you know, you take any continuous time Markov chain, or any Markov process for that matter, and you accelerate it using this accelerating function A. And what that gives you is another Markov process where you can relate the parameters of each one. So here I'm actually writing it out in terms of what are called the infinitesimal generators. So the infinitesimal generator of x will be linked to the infinitesimal generator of z by just multiplying by this accelerating function A, right? So this is a very old result, and this is just a copy of this celebrated book by Struck and Varadan on multidimensional diffusion processes, where they call Volkonsky's result, from a purely probabilistic point of view, the most satisfactory resolution of a martingale problem, which we will present, with the possible exception of Ito's method. Okay, so I'll explain that in a bit. And they're very amazed that they can get away with this construction without needing anything from the theory of partial differential equations. And unfortunately, they're not able to get off so lightly when insisting on being more ambitious. So what I would propose is to be a little bit more ambitious, of course. And one simple way to do that is to introduce immigration into the model. So besides people reproducing at a certain constant rate, which I'll also call lambda, say j minus 1 immigrants will come into the population with probability mu of j minus 1, where mu and nu are just these offspring and immigration distributions, which are just non-negative numbers summing up to 1, right? So what I do to transform simple stochastic processes into this more complex population dynamics model is to consider two independent random walks with the same total jump intensity, whereas the jump sizes will come from these offspring and immigration distributions. And all the thing I need to do is to solve this new equation, which features the new independent continuous time random walk, right? So this is really like the equation we just posed. And at the generator level, what I want to point out is this very interesting relationship between the generators. So the generator of z is an affine function of the state, which we're considering. And the coefficients of this affine function are just the generators of x and y. So these types of time change results had not been considered in the literature until we became interested in them about a decade ago. So, of course, now I've been talking about continuous time random walks. Why? Because they're piecewise constant. And because they're piecewise constant, I can trivially solve this equation, right? But this might become more complicated when instead of continuous time random walks, I use Levy processes. So for example, I could use a Brownian motion in here and there's subordinator over there, right? And that turned out to be the challenge. So let me give you a theorem that we proved together with Maria Emilia Caballero and José Luis Pérez Garmendia back in 2013. And what we do is exactly that. We consider x and y to be independent Levy processes for technical reasons, and we need to assume that x has no negative jumps and that y is a subordinator. And that it turns out that that implies that they're determined by some parameters, which are the characteristic exponents of these processes. I won't get into details there. But it also turned out that, well, your typical Lévy process has trajectories that are densely discontinuous. So they're really discontinuous objects. Even the continuous Lévy processes, that would be Brownian motion with drift, has very irregular trajectories in the sense that they're not even Lipschitz, right? So when you pose a differential equation such as this one, you cannot use the classical theory to solve it. So the first step to do was to realize that, well, instead of focusing on the random phenomena, we could separate it in two parts and first consider these types of equations, but driven by their typical realizations of these stochastic processes. So I just considered two functions, which are going to be CADLAG, and CADLAG is a French acronym for right continuous with left limit, so continu à droite, limité à gauche. I'm going to assume that the G function is strictly increasing, that the F function has no negative jumps, and because we like populations to be non-negative, I'm going to assume that f of 0 plus g of 0 is non-negative. Then we can prove that there exists a unique function h which satisfies this time change equation, which is the same as this one, right? But driven by f and g, right? Good, so that's a theorem that it's very surprising because it's an ordinary differential equation whose drivers can be densely discontinuous, and if not, super irregular. Good. So how did we prove this theorem? Well, this is going to be the only applied part of the talk. We did this by doing a lot of numerical experiments and coming up with a numerical observation, and that's this one. So here are kind of your equation, your time change equation, driven by Brownian motion and by the simplest subordinator possible. So how can you solve this equation? Well, I mean, you can just apply Euler's method to it, right? So that's what we did over here with two different values of delta. So we consider a delta 1 less than delta 2. And as you can see, here are the solutions, Z, right? They look like kind of shifted, slowed down versions of each other, as they should, because they satisfy this equation. But otherwise, they're very entangled, and it's not clear what you should do to relate them. It turns out that what you should do is notice that this equation is actually a differential equation for the integral. So call the integral C, plot it, and you realize that there's some kind of monotonicity that persists under different realizations of the Brownian motion, under all different kinds of drifts. So there should be a theorem saying that, and that's the theorem I'd like to present. So this is the monotonicity result that we proved. We're going to consider two solutions of this equation, one driven by f and g, and the other one driven by f tilde and g tilde. And we're going to call, well, h and c, they come as a pair, right? H is the derivative of c, or the right-hand derivative, because you have discontinuous functions, but they're nonetheless right continuous. And what this theorem says is that if either g is strictly increasing, then if they're ordered, f is less than f tilde, or g and g is less than g tilde, then automatically c is less than c tilde. And what this also automatically does for you is give you an existence and a uniqueness result. Uniqueness is obvious, right? You just take g equal to g tilde, apply this thing twice, noticing that it's symmetric, and then you immediately get that c equals c tilde, which gives you uniqueness. Existence is based on another observation that, well, you require only one to be strictly increasing, but then you can set the other one to be piecewise constant, solve the equation for the piecewise constant case, and then just take limits to solve the equation in the limit, right? So this is the basic strategy to prove these types of existence and uniqueness results. So of course, when x is a Brownian motion and y is the simplest subordinator possible, we already see some pictures of what they look like. And this turns out to give us a construction of a very celebrated process in stochastic analysis, and that would be the squared Bessel process. There's also some other results that we can get, but I think I just drew a picture of this one, so that's the only one for which I'm allowed to talk. Good. So this kind of monotonicity results give you something else, which is unavailable in typical stochastic analysis, a really robust approximation theorem. No matter how you approximate your drivers, right? And if they're continuous drivers, you should think of approximating in a way that's a kind of uniform convergence on compact sets. If your drivers are densely discontinuous, the best thing you can do is to use what probabilists call the Scarha-J1 topology. And then if H is any solution, is the solution to your time change equation driven by f of g, and Hn is a solution to the time change equation driven by Fn and Gn, which could be piecewise constant, for example, then automatically your Hns converge to the solution, and also your integrals, your Cns converge to the integral of the solution, right? So this is a very strong approximation result, and I repeat, it's really not available in the stochastic analysis setting. So of course, stochastic corollaries, if you take any continuous time random walks which approximate your Levy processes, and you solve your population dynamics model, then your solutions converge to what are termed continuous state branching processes with immigration, which are solutions to this driven by X and Y, sorry. And as a corollary, which is more for the probability audience, we can see that CBIs are limits of scaled sequences of Bienemig, Galton-Watson processes with immigration. Good. So I'm going to skip this part because I think there's just about 10 minutes left. Good. And pass to the second result, which has a more French flavor. So I'm going to go back into the past now and recall a 1940s goal, which was to construct Markov processes Z, say on R, you could also pose this problem in Rn, even in infinite dimensions, to construct Markov processes whose generator is a second order differential operator, right, given by 1/2 A times the second derivative plus B times first derivative, where A is the diffusion, it's actually the square diffusion coefficient, and is therefore non-negative. So what's very well known is that in 1942, Ito proposed the following. You define the stochastic integral, and I'm not going to define it right now, don't worry. The Ito stochastic integral, you solve this stochastic differential equation, and the solution under some conditions on A and B is going to exactly solve this problem. So here's what's not known, what remained hidden from 1939, 1940 until the year 2000. So this is Wolfgang Doblin, a German mathematician who emigrated to France and was actually educated there, got his PhD from France, and then actually died a very tragic death in 1940 because he wanted to, fight for France and was being cornered by the Germans and, well, decided to end his life. Before that, though, he had a couple of months where the situation was not quite as tragic and in which he could actually do some mathematics. So he wrote this very long manuscript and sent it to the Academy of Sciences as a sealed envelope. So he sent the sealed letter, and that letter was just forgotten about from 1939, and the rules of the Academy of Sciences said that it could not be opened unless 100 years had passed, or the family was okay with that. And it was actually another French mathematician, Marc Yor, who convinced the family to open this, and surprise, he had an alternative construction for these solution to this problem. So what he proposed, it's more or less the following. If you want to construct a diffusion with this generator, what you do is you take a Brownian motion and you solve this time change equation, which is like the ones we had before, except that before our B was constant, right? And yeah, our A was the identity. Of course, he actually didn't do that. He did, some other things, and also it was a very, it was only a manuscript, right? No actual theorems there. And so we tried to kind of focus on this problem and solved it. I think, well, it's actually work in progress. We haven't made it public yet, but now we have a solution to this. So again, what we do is first a deterministic analysis. So f here is going to be the typical trajectory of b, so it's going to be any continuous function. And we're going to take these coefficients a and b, which satisfy the following. First of all, I want to handle also diffusion with boundary conditions. And so I just assume that there's an interval on which a is greater than 0 on the interior, and a is 0 on the exterior of this interval. Second, just for simplicity, I'm going to assume that f and b are continuous, and a is continuous on this interval. 3, I want this diffusion to remain in the interval, and so if this interval has endpoints, if this interval is finite, I'm going to assume that the drift points inward. Finally, I'm going to do some regularity assumptions. Either b over a is Lipschitz, or b is greater than 0, and a over b is strictly increasing. So this should remind you of monotonicity assumptions and monotonicity results that we just explained. This one is just a classical Lipschitz assumption that just simplifies analysis. Then, under these assumptions, we can find an h that satisfies this general time change equation. Second, the solution remains in the interval I forever. And third, we have approximation. If fn is continuous, fn converges to f. And, well, this could be some discretization parameter if you want to apply the Euler's method. And if not, you just set it to 0. And assume that hn solves the time change equation driven by fn with coefficients a and b. Then automatically hn converges to h. So actually, this turns out to solve the first goal if I just tell you of a theorem that we proved just very, very recently. You can assume all this, or you can assume the following. Assume just that a over b is bounded and measurable. Then the conclusion, at least one, holds. Just under assumption b over a bounded and measurable. So we can actually solve this goal of doing regularization by noise with multiplicative noise. Okay, so it's only one-dimensional, but it's the first step. Good. So I should wrap up, probably. And I can wrap up with another example, which features discontinuous coefficients, and which is actually has been published. Simplest discontinuous coefficients would be indicator functions. So here's indicator of 0 infinity, indicator of 0, right? So x here is going to be any Lévy process, with non-negative jumps. Theta is going to be any positive number because we want this theta to make the diffusion remain non-negative. And the deterministic theorem here says that if f is Cadillac with no negative jumps and starting at a non-negative position and a certain technical condition, which I'm not even going to explain, holds, then for any positive theta, we can build a solution to this equation. And the solution, when f is your typical Lévy process, turns out to be what's called a sticky Lévy process. So that's a process that behaves like your Lévy process when it is positive, and when it reaches 0, it gets kicked back into the positive half line, except that the amount of time that it passes at 0 is positive, right? So that's behavior that's not typical of your Lebesgue processes. And if you think of Brownian motion, the zero set of Brownian motion has Lebesgue measure 0, and yet we're manufacturing a kind of Brownian motion which spends positive time at 0. And that's called, of course, sticky Brownian motion. And it was one of Feller's most amazing discoveries around the 1940s to find this sticky behavior. Good. So we can construct sticky Lebesgue processes using this technology of time change equations. And of course, we can do this also in multiple dimensions. And my kind of most important project right now is to do it in an infinite dimension and consider some types of stochastic partial differential equations which have a time change flavor. And that's all. Thank you very much.
Questions?
So sorry, maybe you discussed a little bit about it, but what happens for your theorem in higher dimensions? So what happens if you want to solve it?
Good. So in high dimensions, so for example, one thing we actually did was to prove existence, uniqueness of time change equations for continuous state branching processes with immigration of multiple types, right? So we can find solutions in Rn. And we do that also by something that has surprised experts, which is proving monotonicity results or comparison principles, as they're called in the PDE setting, in this multidimensional setting. So yes, you can kind of, we provided an example for how to do this multi-dimensional extensions, right? Of course, now what we're really interested in is in doing a more systematic attack on this problem, right? Another thing that is interesting is how to build time change equations, for example, for matrix valued processes. And one interesting instance of that would be Wishart processes. Why? Because the SDEs, nobody has been able to prove pathwise uniqueness, and yet we might be able to prove existence and uniqueness using these time change equations. So that's another very interesting challenge I see.
So your existence and uniqueness is strong existence and uniqueness? Or?
Okay, so no, you can prove weak existence and uniqueness. Sometimes in some parameter regimes you can prove pathwise uniqueness, but in the parameter regimes that you expect there to be pathwise uniqueness, there's not been a technique that has been able to prove that.
Thank you.
Mm-hmm.
I have a question. Do you consider a possibility to make it third order by differentiating and taking the chain rule? But maybe then you will have an equation without the integral.
So that's a very interesting and intriguing question. So far we haven't tried because the differential operators that are associated to stochastic processes are typically of the second order, right? Now there are some non-Markovian stochastic processes for which you could try and do that. Iterated Brownian motions are the kind of things you could try. We haven't, but thank you for the suggestion.
Okay, so I think maybe it's... there is a last question? No? Yeah. Yeah, it already... Anyway, okay, so let's thank Jerónimo again and all the speakers of the morning. And, well, we'll continue tomorrow.